What if the Earth itself answered a cosmic event? Just hours after interstellar object 3 Atlas crossed the Sun's meridian, a moment of perfect alignment, deep seismic sensors in the Pacific began to hum. Not an earthquake at first, but a pulse. Harmonic tremors beneath Tonga. Then another, thousands of miles away under Chile's coast. Two opposite ends of the same ocean, vibrating in rhythm. At the same time, solar wind readings showed strange fluctuations. Magnetometers twitched, ionospheric data spiked. Could this be chance? Or the first sign of something connecting space weather to Earth's crust itself? Some say it's coincidence. Others whisper it's coupling, energy echoing between the sun, an interstellar visitor, and our planet's deep heart. Stay until the end, because what follows may challenge not just science, but the boundary between the cosmic and the terrestrial itself. 3I Atlas, strange interstellar visitor. It arrived from the black, silent gulf between stars, moving too fast to be bound by the sun's gravity, yet tracing a path so deliberate that astronomers couldn't look away. Designated 3I Atlas, it was the third confirmed interstellar object ever detected, a traveler from beyond our solar neighborhood. But what puzzled scientists wasn't just its origin, it was what it did as it approached the sun. Its surface reflected light unevenly, like polished metal under drifting dust. Spectral scans showed a bizarre nickel-to-iron ratio far beyond what's typical for comets or asteroids. Some suggested it was an exposed fragment of a destroyed planet. Others whispered about artificial alloys. When first discovered by the Asteroid Terrestrial Impact Last Alert System in early 2025, it appeared faint and unassuming. But within weeks, telescopes began registering unpredictable brightening, outbursts too strong to be explained by solar heating alone. The object was venting material, but the jets weren't coming from the sunward side. They were directed forward, almost as if it was propelling itself. That forward-pointing jet defied every known model of cometary behavior. Astronomers at the European Southern Observatory noted something else: polarization anomalies. The light scattering off 3I Atlas didn't match the pattern expected from dust or ice. Instead, it hinted at microstructures capable of reflecting light in a controlled pattern. At first, the data was quietly reviewed, then quietly buried in internal memos. Too strange, too uncertain, too much like the wild claims that followed Oumuamua years before. But outside the official reports, the whispers began. Another interstellar object behaving like it knew where it was going. By mid-2025, its trajectory had been refined. Hyperbolic, inbound, and on course to cross the sun's meridian, a rare alignment where Earth, Sun, and the object form a straight celestial line. Normally, such geometry is just orbital trivia, but this time, something changed. Around the date of that alignment, magnetometers across the solar system started to pick up faint irregularities. It wasn't a flare or a CME, just a subtle drift, as though a hidden current had brushed past the sun's magnetic field. NASA's Parker Solar Probe recorded a faint, oscillating wave pattern, neither solar wind nor cosmic ray signature. Scientists labeled it undetermined plasma event, though the coincidence with 3I Atlas's trajectory didn't escape notice. A few independent researchers began to map the event timeline, and what they found made them uneasy. Within hours of that meridian crossing, seismic sensors half a world apart, beneath Tonga and off the coast of Chile, began to hum with deep harmonic tremors. No mainstream publication linked them, no agency made the connection publicly. But on message boards frequented by geophysicists and heliophysicists, the question emerged. Could something about that cosmic alignment have triggered the Earth itself? Could a pulse of energy from the sun, or from the interstellar visitor passing near it, somehow couple with our planet's crust? To entertain the idea requires crossing the boundaries between disciplines, astrophysics, seismology, and electromagnetism. But nature doesn't follow departmental rules. Earth is, after all, an electrically active body orbiting within a vast magnetic sea. Solar wind particles constantly stream against our magnetosphere, compressing, twisting, and vibrating it. When those oscillations intensify, they can induce currents deep within the ground. Usually they're too weak to matter. Usually. The Tonga subduction zone, one of the most active on Earth, already exists in a delicate balance of immense forces. A minor shift, electrical, magnetic, or gravitational, could, in theory, disturb stresses miles beneath the ocean floor. The tremors detected after the alignment weren't surface quakes. They were deep harmonic resonances, the kind that suggests slow, rhythmic stress release rather than sudden rupture. Chile, thousands of miles away but on the same Pacific tectonic arc, registered an almost identical pattern hours later. Coincidence? Possibly. But coincidences have structure. The tremor frequencies match nearly 0.3 hertz apart, a resonance interval eerily similar to certain Schumann harmonics in Earth's ionosphere. Those frequencies, shaped by global lightning and magnetic interactions, can fluctuate during geomagnetic disturbances. When a strong solar event occurs, they sometimes intensify, and on that day, the sun had briefly flickered, not enough for an official flare classification, but enough to cause a measurable uptick in solar wind density. If these events were connected, it would mean something remarkable. The alignment of an interstellar body, the sun's magnetic pulse, and Earth's crustal response formed a single resonant chain. To skeptics, that's pure numerology. To others, it's a hint of a deeper physics, one that ties cosmic motion to terrestrial rhythm. Even more unsettling was the timing of the data blackout. Several satellite feeds monitoring magnetospheric flux went offline for maintenance just as the anomalies occurred. When the data resumed, the baseline had shifted slightly, just enough to complicate reconstruction. Analysts at a private geomagnetic observatory in New Zealand claimed to detect a short-lived microcurrent surge during the same window, describing it as a coherent, low-frequency wave passing through the southern Pacific magnetic shell. It lasted less than 40 minutes, yet its timing aligned perfectly with 3I Atlas crossing the sun's meridian. The scientific community remained cautious. But in online circles, where space weather enthusiasts overlap with seismic researchers, charts and overlays began to appear. Magnetic field deviation against seismic amplitude, solar wind density plotted over tremor depth. The graphs didn't prove anything, but the symmetry was haunting. If there is a link, what could cause it? Some theorized electromagnetic coupling. The same charged particles that shape auroras might induce piezoelectric stresses in mineral-rich oceanic crust. Others looked deeper, suggesting gravitational microresonance, the idea that even a small external force can synchronize with internal oscillations if timed perfectly. 3I Atlas's trajectory, slicing across the sun's equatorial magnetic current sheet, could have acted as a catalyst, amplifying waves already propagating through interplanetary space. In earlier centuries, such thoughts would have been dismissed as superstition, linking comets to earthquakes. But modern instruments have begun to reveal what ancient intuition guessed, that energy moves through the cosmos in waves, some seen, some unseen. The Tonga-Chile coincidence may not mark the start of a new physics, but it challenges the neat separation between sky and ground. Meanwhile, 3I Atlas continued outward, silent and inscrutable, leaving behind a trail of plasma and speculation. Astronomers still debate whether it was a fragment of something ancient, a planetary core stripped bare, or an engineered relic of a civilization lost to the void. Its brief passage through the inner system raised more questions than it answered. And yet the deeper mystery may not be about what 3 Atlas is, but what it triggered. Because in its wake, subtle echoes continued. Weeks later, magnetometers in Antarctica recorded new harmonic bursts, low-frequency oscillations that mirrored those detected during its crossing. In Tonga and Chile, smaller tremors recurred, weaker but patterned. Patterns. That's what keeps investigators awake. A pattern repeating across space, the sun and the earth, hints that the universe might be more connected than we think. Perhaps the cosmos speaks through resonance, and every once in a while, something passing through, something like 3I Atlas, strikes the right note. Scientists will continue to debate whether these events mean anything. Data will be refined, correlations reanalyzed, probabilities recalculated. But for those watching the night sky and listening to the Earth's deep hum, the feeling remains. Something passed close, and for a moment, the planet responded. A whisper beneath the Pacific, a pulse from beyond the stars. Crossing the sun's meridian, timing and geometry. Every celestial body follows its own path, yet sometimes those paths intersect in ways that feel deliberate, almost choreographed. When 3I Atlas crossed the sun's meridian, it wasn't just another point on a plotted orbit. It was a moment of perfect alignment. Earth, the sun, and an interstellar object locked in a single invisible thread across space. Astronomers mark such events casually as routine geometry. But the consequences of this one refused to stay quiet. At precisely 11:42 UTC on the day of alignment, the interstellar traveler's position projected directly over the sun's central meridian, the imaginary line dividing the sun's disk when viewed from Earth. It was a fleeting configuration lasting barely hours, yet across multiple observatories, solar instruments began reporting subtle irregularities in the solar wind. The flow wasn't faster, just structured. Wave packets repeating with unusual periodicity, as though something beyond the sun's surface was modulating its breath. Normally, these patterns might be dismissed as noise, but timing is everything in celestial mechanics. The sun's meridian crossing coincided with a region of magnetic calm. No sunspots, no flares, a nearly spotless disk. That made the faint rhythmic fluctuations stand out all the more sharply. It was as if the sun, usually a turbulent ocean of plasma, had momentarily hummed a note no one expected. To grasp the geometry, imagine a straight line stretching from the heart of the sun to Earth and extending far beyond. For a few hours, 3i Atlas traced that same line. From a heliophysical standpoint, it meant that the interstellar object passed through the sun's heliospheric current sheet, a vast undulating plane of magnetic polarity reversal, the so-called cosmic neutral sheet, where the solar magnetic field flips. It's a volatile zone filled with plasma discontinuities, a place where electric currents arc across millions of kilometers. Crossing it during near-perfect alignment meant the object wasn't just in visual symmetry, it was threading through the sun's electromagnetic heart. That raised questions few dared to ask publicly. Could an object of unknown composition, moving at interstellar speed, briefly interacting with the sun's current sheet, generate disturbances that propagate outward, disturbances that Earth might later feel as geomagnetic tremors? The alignment was calculated with precision. Orbital data from JPL's Horizon system confirmed that at the moment of crossing, 3i Atlas was 0.82 AU from the Sun, inside the range where solar flux begins to significantly alter a body's ionized envelope. As sunlight struck its surface, it released streams of charged particles, forming a thin, fake forward-tilted coma. But instead of dispersing, the coma appeared to maintain coherence, behaving like a magnetic sheath. That sheath, interacting with the solar magnetic plane, may have produced small electromagnetic ripples that radiated outward along the very line that led toward Earth. At the same time, Earth's magnetosphere was in a rare state of stability. For nearly 2 weeks prior, no significant solar storms had occurred. Satellite telemetry recorded low proton flux and minimal geomagnetic indices. Then, just as the alignment peaked, faint perturbations appeared in the DST index, barely measurable, yet synchronous across multiple observatories. The perturbations lasted 40 minutes. Afterward, seismographs under the Pacific began to register harmonic tremors, deep, slow, rhythmic. Coincidence, perhaps, but the geometry made the timing too precise to ignore. The alignment line passed through the Pacific hemisphere of Earth, intersecting the very region later struck by those deep tremors. Tonga and Chile. Both lie near 19 degrees S latitude, directly under the sun's subsolar point that day. It was as if the energy, magnetic, electromagnetic, or something subtler, had traveled down that meridian line, intersecting the crust where the planet was most exposed to solar coupling. Solar physicists call this the subsolar focusing effect. When the sun's field orientation couples most directly with Earth's magnetosphere, field lines can briefly open, allowing energy exchange. Typically, this happens during strong solar wind events. But in this case, there was no storm, no CME, no visible reason for any exchange at all. The only variable that changed was geometry. In cosmic dynamics, geometry is destiny. Alignment doesn't create energy, but it channels it. When planets align, gravitational forces combine linearly. When magnetic axes align, current paths straighten. For brief moments, invisible conduits form, pathways through which charged particles and electromagnetic waves can travel farther and faster. Most of the time, these conduits pass unnoticed. But when the conditions line up perfectly, a stable solar field, a conductive interstellar object, a quiet magnetosphere, even a subtle pulse might propagate across the system like a tuning fork strike. At least, that's what some independent researchers began to propose. A small group of heliophysicists from Japan and Finland ran simulations showing that an electrically charged body crossing the sun's current sheet could induce a temporary reconnection event, releasing a low-frequency plasma wave outward. Their models suggested such a wave, though weak, could reach Earth's vicinity in a few hours and modulate ionospheric currents. Those currents, in turn, could resonate with tectonic stress fields under certain conditions. It wasn't proof, just a tantalizing model. Mainstream institutions avoided the topic. The official solar observatories labeled the event geometrically interesting, physically trivial. But a few quiet data points told a different story. The Solar Dynamics Observatory logged a transient radio spike near 2 MHz, far below typical solar emissions, lasting less than a minute. Simultaneously, ground-based receivers in Hawaii and Chile noted minor deviations in VLF, very low-frequency signals passing through the ionosphere. None of these anomalies were dramatic, yet all shared the same timestamp, within 20 minutes of the Meridian crossing. It's easy to dismiss single anomalies, but patterns, even faint ones, demand attention. When those patterns mirror geometric alignments, they become hard to unsee. By nightfall, 3I Atlas had already moved past the Sun's meridian, heading into the outbound leg of its hyperbolic path. Astronomers noted that its coma appeared slightly polarized, an effect hinting at strong electromagnetic interaction. Its photometric curve flattened, suggesting the release of a charged halo. And still, deep beneath the Pacific, the tremors continued, fading over hours like the echo of a bell. Some theorists proposed an even stranger mechanism: resonance synchronization. Earth, they argued, isn't just a passive receiver of solar energy, but part of a resonant system spanning the heliosphere. The alignment of a massive interstellar object could temporarily shift that resonance, nudging oscillations already present within Earth's crust. Think of it as plucking one string in a cosmic instrument and hearing another vibrate in sympathy. Skeptics countered with simpler explanations: deep subduction slip, tidal stresses, or random coincidence amplified by human pattern seeking. Yet even skeptics admitted that the timing was remarkable. The Tonga and Chile tremors didn't behave like typical tectonic events. They were too harmonic, too global in symmetry. Throughout history, alignments between celestial bodies have inspired both superstition and scientific curiosity. The ancients watched planets line up and felt the world tremble long before they knew why. Today we have instruments, magnetometers, seismographs, space probes, that can quantify those tremors, measure those flickers. And still, the deeper link remains elusive. The crossing of the Sun's meridian by 3 Atlas may one day be seen as an ordinary orbital event. But to those who followed it live, astronomers watching the Sun's face, geophysicists watching the Earth's pulse, it felt different. There was a sense of tension in the data, a rhythm connecting sky and ground. Perhaps it was nothing. Perhaps it was everything we've yet to understand. Because in the language of the cosmos, alignment is rarely silent. It hums, it resonates, it leaves traces. And as 3 Atlas drifted back toward the void, the instruments it stirred kept listening. To the sun, to the earth, and to that invisible line between them where for a brief moment something may have whispered through the solar wind. A whisper that sounded less like coincidence and more like connection. Space weather as a trigger. Solar flares, coronal mass ejections, CMEs. Every storm on Earth begins with a trigger, a shift in pressure, a spark in temperature, a change so small it almost escapes notice. The sun is no different. Its storms, invisible yet immeasurably vast, begin with tremors of plasma, threads of magnetic tension winding tighter and tighter until they snap. When that happens, the sun releases titanic bursts of energy, solar flares and coronal mass ejections or CMEs. For most of human history, these were unseen. But now, every satellite and probe that watches our star knows. When the sun shivers, the entire solar system feels it. During the period when 3I Atlas crossed the sun's meridian, something peculiar happened. The sun was quiet, too quiet. Cycle 25, expected to rise gradually, showed a lull. Instruments like SOHO and SDO recorded low sunspot activity, no major flares, no CME alerts. Yet Earth's magnetic field told another story. A faint, slow disturbance rippled through the magnetosphere. Measurable, structured, but without a visible solar source. Scientists call these stealth CMEs, eruptions that escape traditional detection, leaving only fingerprints of magnetic rearrangement in their wake. It was as though the sun had exhaled invisibly. And the timing, within hours of 3 Atlas's solar alignment, raised questions no one wanted to voice in print. Could the interstellar object's passage have influenced solar stability? Could it have plucked the sun's magnetic strings, setting off a silent reverberation that reached Earth's shield? To understand why this question matters, we need to revisit how space weather truly works. Solar flares release bursts of radiation, X-rays, gamma rays, and ultraviolet light, traveling at light speed. CMEs, on the other hand, hurl charged plasma clouds through space, moving slower but carrying immense magnetic power. When they hit Earth's magnetosphere, they compress it like a balloon in wind. The energy they deposit doesn't vanish, it sinks into the ionosphere and even deeper into the conductive veins of the crust. Most of the time, the planet absorbs these shocks harmlessly, but under the right conditions, certain magnetic orientations, certain densities, the effects compound. Auroras ignite, radio signals falter, satellites glitch, the haze, and deep beneath the surface, faint electrical currents surge through rock and metal. These telluric currents can alter stress in fault zones. They can even change the frictional properties of minerals, subtly modulating how Earth's crust behaves. For decades, geophysicists dismissed the idea that solar storms could trigger earthquakes, but data has begun to whisper otherwise. Studies from Japan, Italy, and Russia have shown slight upticks in seismicity following major geomagnetic storms. Not everywhere, not always, but in specific regions already near critical stress. It's as if the Earth's crust sometimes waits for an external nudge, a signal to release tension. During the 2025 Meridian crossing, Earth's instruments recorded that faint nudge. A small uptick in solar proton flux, just enough to be statistically significant, passed across our planet's dayside magnetosphere. No major flare was seen, but spacecraft on the L1 point noted irregular plasma densities in the solar wind. These fluctuations arrived 3 hours after 3I Atlas crossed the sun's equatorial current sheet. Coincidence? Perhaps, but the pattern matched past stealth CME timelines, where the source region emitted no visible coronal signature. Meanwhile, deep-sea seismographs off Tonga began registering low-frequency tremors, resonant and rhythmic, unlike typical tectonic slip. The same day, magnetometers in Chile detected ground currents 10% above baseline, tiny but measurable. Local power grids experienced momentary harmonic distortions. To the untrained eye, it was nothing. To researchers tracing cosmic timing, it was a clue. Solar weather is not simply radiation, it is information, encoded in charged particles and magnetic flux. Each CME carries its own magnetic signature, its polarity, its twist. When that polarity opposes Earth's field, it couples efficiently, opening portals through which energy flows directly into the upper atmosphere. During 3I Atlas's crossing, the polarity orientation was southward, the same direction that most efficiently interacts with Earth's magnetosphere. For a few hours, geomagnetic reconnection intensified, allowing more current to flow between space and Earth. This invisible bridge, stretching from the sun to Earth's crust, is what some researchers now call the solar terrestrial circuit. Its existence is not speculation. Satellites and ground arrays record its currents daily. But the possibility that something external, an interstellar object threading through the sun's electromagnetic sheet, could temporarily alter that current, that's the frontier no one dares to explore openly. Yet whispers circulate among heliophysicists that interstellar objects carrying their own charged plasma envelopes could perturb local fields when passing through magnetic nodes. Not drastically, not catastrophically, but subtly, enough to tweak the phase of solar oscillations or disrupt the balance of the heliospheric current sheet. 3I Atlas, moving at extraordinary velocity and showing a forward-directed jet, might have acted like a moving conductor in a charged ocean. Even a minor perturbation there could ripple outward. To the layperson, this sounds speculative, but in plasma physics, resonance matters. The sun's magnetic oscillations have natural frequencies, so does the Earth's magnetosphere. When they align, or are forced into alignment, energy transfer becomes exponentially more efficient. If a passing object adjusted that alignment, even by fractions of a degree, it could momentarily amplify the coupling between sun and Earth. And during that window, the magnetosphere's gentle hum could become a low global vibration. The result wouldn't be a surface catastrophe. It would begin quietly, Subtle ionospheric heating, faint Schumann resonance drift, changes in subcrustal current. Over time, those oscillations could synchronize with tectonic stress fields, nudging them closer to release. And where does that happen first? In the Pacific, the world's seismic heartbeat. Tonga and Chile sit like tuning forks on opposite edges of the same vast plate. When one hums, the other listens. Historical records show strange synchronicities. In 1859, the Carrington event, the largest solar storm in recorded history, struck Earth. Within days, reports of earthquakes increased globally. In 1972, an M6 flare coincided with deep tremors under Japan. In 2003, the Halloween storms preceded unusual seismic swarms near the South Sandwich Islands. None of these prove causation, but the timing, again and again, draws attention. Space weather as a trigger doesn't mean the sun causes quakes. It means that under specific alignments, energy from above might interact with tensions below, amplifying processes already underway. It's the final nudge on a locked door. In the aftermath of the 3 Atlas Meridian event, global geomagnetic indices spiked modestly, yet the auroras that followed were abnormally deep red, a color seen when high-energy particles penetrate lower into the atmosphere. Observers in Tahiti and Easter Island captured faint glows never seen so close to the equator. That implied unusual energy penetration, perhaps through a temporarily weakened magnetic field. If such penetration reached the ionosphere, it could alter conductivity in the equatorial electrojet, a fast-moving current looping around the planet's waist. Changes in that current are known to produce induced ground currents thousands of kilometers apart. Tonga and Chile, both near the magnetic edges of that band, could have been the most sensitive receivers. The tremors that followed may have been the crust's way of discharging that new tension. Of course, the official reports never mentioned 3I Atlas. The explanation remained localized subduction activity. No connection to solar weather, no acknowledgement of timing. Yet in data archives, the stamps remain, one celestial, one terrestrial, overlapping to the minute. The next day, solar wind normalized. The Earth quieted. 3I Atlas continued outward, its plasma sheath dimming as it left the sun's influence. But for a moment, something had synchronized. The sky, the sun, and the deep Earth had resonated together. Space weather has always been treated as a threat to satellites and power grids, never to the planet itself. But what if it's more than that? What if the Earth, like a living organism, responds electrically to solar rhythm? What if alignments like the one with 3I Atlas amplify that rhythm, transforming space weather into a planetary heartbeat? That question is what lingers, because the tremors that followed were not violent, but harmonic, steady, repeating, musical. As if somewhere deep below, the Earth wasn't breaking apart, it was answering back. Deep tremors. Beneath Tonga, ground geology of Tonga subduction. Far below the Pacific surface, where sunlight dies and heat begins to whisper through stone, the Earth folds in on itself. The Tonga subduction zone, one of the deepest and most active geological scars on the planet, is where the Pacific plate dives beneath the Indo-Australian plate at a staggering rate of 24 centimeters per year. It's a boundary between worlds, the brittle crust above and the convecting mantle below. But in early July 2025, when interstellar object 3I Atlas crossed the sun's meridian, something in this hidden realm stirred. At first, the signals were faint. Deep seismometers positioned along the Tonga Trench, part of a multinational ocean bottom monitoring network, began registering tremors. Not the abrupt spikes of normal earthquakes, but long harmonic oscillations, deep, slow, rhythmic pulses. The frequencies were between 0.5 and 1 hertz, a range often associated with slow slip events, movements too gradual to be felt, but too patterned to be random. What puzzled researchers wasn't their magnitude, but their symmetry. These tremors arrived in clusters, spaced evenly over several hours, almost like a metronome ticking beneath the ocean. And when the timestamps were compared to global magnetometer data, the pulses appeared to coincide with subtle fluctuations in Earth's magnetic field. Nothing catastrophic, nothing dramatic, but enough to make even the most skeptical geophysicists raise an eyebrow. The Tonga subduction zone is a natural amplifier of energy. The Pacific plate here is not only thin and ancient, but also heavily hydrated, saturated with seawater that has seeped through fractures over millions of years. When that slab is dragged deep into the mantle, Those trapped fluids lower the melting point of surrounding rock, making it more pliable. This creates a feedback loop of friction and release, an enormous geological resonator that can hum when triggered. Ordinarily, these triggers come from tectonic shifts or tidal forces, but in July 2025, tides were minimal. No major tectonic rearrangement was detected. The tremors came from a depth of roughly 600 kilometers, too deep for ordinary earthquakes, too shallow for core mantle boundary dynamics. It was as if the slab itself had begun to sink. To understand why this region responded first, you must picture the Tonga Trench as a descending arc of stone, an immense curve where the crust bends downward into the mantle. As the slab sinks, it occasionally sticks, storing energy like a bent spring. When it slips, it can release that energy in waves that travel laterally for thousands of kilometers. But the events in 2025 weren't normal slips. They had no clear onset or end, no sharp seismic phases. The waves built gradually, peaked softly, then faded like ripples in liquid metal. That drew attention from researchers studying a phenomenon known as deep harmonic tremor, first observed near volcanoes and later in subduction systems. These tremors, though weak, are consistent with the movement of superheated fluids under immense pressure, fluids escaping through cracks within the descending slab. Normally, they mark volcanic unrest or magma migration, but Tonga's deep tremors came from well below any known magma reservoir. Something else had disturbed the crust's balance. Some seismologists proposed a simple explanation: dehydration reactions. As the slab descends, increasing heat and pressure squeeze out water from hydrous minerals, creating localized bursts of stress. Yet these processes are typically gradual, not synchronized across hundreds of kilometers. The timing, hours after 3I Atlas's solar alignment, didn't fit the standard pattern. Others began to wonder if electromagnetic factors could have been involved. Tonga sits near a region of strong magnetic flux variation, a place where Earth's magnetosphere lines converge. During geomagnetic disturbances, induced currents can flow through the crust, especially in conductive regions like hydrated slabs. These currents can alter fluid pressures, potentially triggering microslip or stress redistribution. If even a minor solar-induced fluctuation passed through this region, it might have amplified existing instabilities deep underground. Such ideas border on the speculative, yet precedent exists. In 2008, Japanese researchers documented electromagnetic precursors to deep tremor episodes near the Nankai Trough. The signals, recorded hours before seismic activity, involved ultra-low frequency magnetic waves, similar to those that ripple through Earth's field during space weather events. The Tonga signals from 2025 shared eerily similar frequency characteristics. The Tonga Trench is also unique in geometry. It forms a near-perfect arc curving northwest to southeast, aligning almost directly beneath the subsolar point during 3 Atlas's crossing. For a brief window of time, that section of ocean was magnetically illuminated, the sun's electromagnetic field lines intersecting Earth's surface most directly. If any coupling effect existed between the sun and Earth that day, Tonga would have been the first receiver. The tremors deepened over the next 8 hours. Their waveform consistency led some analysts to describe them as musical, a repeating resonance at specific intervals, 3.6 and 7.2 minutes apart. These intervals correspond suspiciously to known magnetospheric pulsation bands, PC5 waves, oscillations in the Earth's magnetic field driven by solar wind pressure. Could it be coincidence that the deep Earth and upper atmosphere vibrated at nearly identical frequencies? Or had something truly linked them, briefly synchronizing heaven and Earth in one resonant hum? In the data logs, another anomaly appeared. Hydrophones, underwater microphones used to monitor oceanic quakes, picked up faint infrasound bursts preceding each tremor. The bursts were too low in frequency for any human ear, but they followed a consistent pattern: a buildup, a peak, a drop. Infrasound of this nature has been recorded following ionospheric disturbances, often when charged particles collide with atmospheric layers and transfer energy downward through the air column. That kind of coupling had been theorized, but never documented so cleanly over an oceanic trench. Satellite readings from NASA's timed mission showed slight variations in thermospheric density above the same region, indicating minor heating. Again, too small to make headlines, but perfectly aligned in time. The deeper scientists dug, the stranger it became. One researcher from the University of Auckland described it in a closed-door symposium. It was as if the Earth heard something and answered with a murmur. But not everyone was convinced. The U.S. Geological Survey attributed the tremors to normal subduction processes, pointing to similar deep events recorded in the past decade. Yet the Tonga tremors had one statistical outlier: their harmonic purity. Previous deep tremors displayed chaotic energy distributions. These showed coherence. Something had tuned the slab. The region's geology offered one final clue. Beneath the trench lies the remnant of an ancient microplate, a long-vanished piece of oceanic crust now lodged at depth. This boundary layer, rich in serpentine and magnetite minerals, acts like a natural conductor. When electric currents pass through it, the material expands minutely, generating seismic noise. During space weather disturbances, magnetite-rich regions can behave like antennae, receiving and re-radiating electromagnetic energy. Tonga's subduction system, therefore, isn't just a geological formation, it's an immense planet-scale receiver. If this interpretation holds, the 2025 tremors might represent the first observed instance of cross-domain resonance, where space weather frequencies found a literal echo in the deep Earth, a seismic shadow of solar harmonics. What made this theory so controversial wasn't its plausibility, but its implications. It suggested that planetary geology isn't an isolated system, that beneath miles of rock, Earth might respond, faintly, rhythmically, to changes in the solar environment. To many, that sounded poetic. To others, it sounded dangerous, hinting that large-scale cosmic cycles could subtly influence tectonic behavior. In Tonga, the aftermath was quiet. No tsunami, no eruption, no destruction. But weeks later, a scientific vessel passing through the area reported elevated methane concentrations in seafloor vents, a sign of disturbed sediments. Deep within the subduction zone, stresses had shifted. The region's internal clock had been reset. Meanwhile, 3I Atlas continued outward, its tail diffused into solar wind. The tremors ceased as suddenly as they began. Yet, for days afterward, magnetometers across the Pacific kept recording faint echoes, like aftershocks in the electromagnetic spectrum. Perhaps it was all coincidence, or perhaps for one moment something vast and ancient resonated across scales, from the sun's plasma tides to the hidden pulse beneath the Pacific. Whatever the truth, those who studied the data would later agree on one thing: the Earth felt something that day. A whisper through stone, a pulse beneath the waves, and for a few brief hours, the deepest trench on Earth seemed to listen to the cosmos and respond in kind. Mirrored tremors under Chile, remote coupling, or coincidence. When seismographs in Tonga began to hum that July morning, few expected that nearly halfway across the planet, on the other side of the Pacific, Chile's instruments would begin to do the same. At first, the Chilean data looked unremarkable, a faint, low-frequency vibration deep beneath the Nazca Plate, typical of the subduction environment along South America's coast. But when analysts later overlaid Tonga's records onto Chile's, the correlation was startling. The two tremor sequences, separated by more than 9,000 kilometers of ocean, were almost perfectly synchronized. To geophysicists, that made no sense. The Tonga Trench and Chile Trench are parts of the same vast tectonic boundary, the so-called Ring of Fire, but they don't interact directly. The movement of one slab should take years, even decades, to influence the other. Yet here were deep harmonic tremors, rising and falling in lockstep, within minutes of each other. The coincidence would have been easy to dismiss, except for the timing. Both tremor series began within hours of 3 Atlas crossing the sun's meridian. Both occurred during an otherwise quiet solar period with no strong CMEs or solar flares, and both exhibited the same rhythmic spacing, waves repeating roughly every 7 minutes, the same pattern found in magnetospheric pulsations recorded by satellites orbiting Earth that day. It was as though two distant parts of the planet's crust were vibrating to the same external metronome. The first Chilean anomalies were detected by the Atacama Deep Earth Array, a network of high-sensitivity seismometers buried beneath the desert, designed to capture signals from hundreds of kilometers below the surface. The data showed tremors originating from 550 to 650 kilometers in depth, far below the crust and upper mantle, within the descending Nazca Plate. That's the same depth range as Tonga's deep tremors. Initially, the Chile team assumed instrument error. Low-frequency noise can result from oceanic microseisms or atmospheric interference, but the Atacama sensors are shielded from both. The signals were clean, coherent, and unmistakably seismic. When converted to audio frequency, they produced a deep, resonant tone, eerily similar to the Tonga waveform. As news spread through the seismological community, a few researchers began to run cross-correlation analyses. When they time-shifted the Tonga and Chile tremor data according to Earth's magnetic field lines, the invisible loops connecting the two hemispheres, the peaks aligned even more closely. That revelation caused quiet discomfort in the research chat rooms. It implied something unthinkable, that energy or information might have traveled through the magnetosphere rather than through the crust. The idea of remote seismic coupling via electromagnetic means has long been fringe science. Yet the mathematics of resonance doesn't care about academic boundaries. If two systems share similar frequencies and are exposed to the same external oscillation, they can synchronize, a process known as entrainment. It's the same phenomenon that causes pendulums in the same room to swing in unison, or neurons in the brain to pulse together in waves. Could something similar happen between tectonic plates separated by half the planet? Chile's geology makes the hypothesis even more curious. The Nazca Plate, like the Pacific, is rich in magnetite-bearing rocks, natural conductors capable of interacting with electromagnetic energy. Beneath Chile's Andes lies one of the most extensive subduction slabs on Earth, plunging deep into the mantle. Its curvature, electrical properties, and water content are strikingly similar to Tonga's. Both regions, it turns out, are natural resonators. On July 4th, 2025, one day after the Meridian alignment, ground-based magnetometers in Santiago, Easter Island, and Arica recorded faint but synchronous geomagnetic pulsations. These oscillations mirrored those seen over Tonga's geomagnetic footprint. The correlation coefficient between the two regions exceeded 0.8, extraordinarily high for signals separated by an entire ocean. In simpler terms, the Earth's magnetic shell above Tonga and Chile was vibrating together. This might explain how two distant subduction zones could experience near-simultaneous tremors, not through mechanical transfer, but through shared electromagnetic forcing. When the magnetosphere vibrates in certain frequencies, especially those in the ultra-low frequency band, or ULF, it can induce electric fields in the crust. Those fields, in turn, create microcurrents that alter stresses deep underground. Normally, these induced currents are far too weak to trigger anything measurable. But if a system is near a critical threshold, a tectonic spring ready to slip, even a small modulation could tip the balance. The Chilean tremors had one additional peculiarity. Embedded in the seismic data were subtle amplitude modulations, sidebands spaced roughly 0.05 hertz apart, the same spacing observed in Schumann resonances, which are global electromagnetic standing waves trapped between the Earth's surface and ionosphere. This pattern suggested that whatever had influenced Tonga's crust was also influencing Chile's, through a resonance extending across the entire planet. When data from satellites like Swarm and Themis were analyzed, they revealed that on that same day, the Earth's magnetotail, the long plasma structure stretched behind the planet by solar wind, had experienced a rare wave reflection event. A low-frequency pulse, possibly originating from a minor solar wind density fluctuation, had bounced between hemispheres several times before dissipating. The wave period? 7 minutes, the same as the seismic tremors. For mainstream geophysicists, the simplest explanation was coincidence. But for those who study cross-domain coupling, the interplay between solar, atmospheric, and seismic processes, this was a signal too well-timed to ignore. Even so, skeptics pointed to alternative causes. Deep tremors in Chile could have been triggered by subduction fluid migration or slab bending stresses, perfectly natural processes. Some even proposed that Tonga's and Chile's events were independent responses to similar tidal stresses caused by the moon's position that week. Yet the moon's gravitational influence doesn't operate on 7-minute cycles, nor does it create synchronized magnetic pulsations. Still, the timing of 3 Atlas loomed over every discussion. At the exact hour of the sun's meridian crossing, the object was passing through the solar magnetic equator, the most electrically dynamic region in the heliosphere. Some theorists speculated that it could have caused a micro-reconnection event, releasing a faint burst of magnetized plasma that propagated along interplanetary magnetic field lines. When those lines intersected Earth, they might have transmitted a low-frequency oscillation through the magnetosphere, one that resonated with the planet's natural frequencies. If true, it would represent the first known case of interstellar-induced magnetoseismic coupling, a phrase that sounds more like science fiction than science, yet the data refuse to stay silent. In Chile, seismologists at the Universidad de Concepción began calling it El Espejo Sísmico, the seismic mirror. Not because the tremors were identical in magnitude, but because they reflected each other's rhythm, like two sides of a vibrating drum. Over the following days, more anomalies surfaced. GPS stations in both Tonga and Chile recorded subtle vertical displacements, mere millimeters, but synchronized. Atmospheric sensors detected short-lived disturbances in the ionospheric total electron content above both regions, hinting at shared electromagnetic forcing. And when spectrograms of the tremor waveforms were combined, the result was uncanny, a mirrored symmetrical pattern spanning the Pacific Basin. The Pacific, in this sense, became a resonant cavity, a giant amplifier linking two of Earth's deepest subduction systems. It's possible that energy from one side reflected through the planet's interior, bouncing between density layers like sound in a bell. But the travel time for such waves doesn't match the data. The near instantaneous response points to something faster than seismic propagation, something electromagnetic. By the week's end, the tremors faded. Tonga's deep resonance quieted, and Chile's harmonic pulses diminished to background noise. The Earth returned to stillness, but the data remained, a record of synchronous activity stretching across one of the widest distances on Earth. When the International Review paper was drafted months later, the authors softened their language, anomalous temporal coincidence between Pacific subduction zones during heliospheric alignment, they wrote. No mention of 3I Atlas, no mention of magnetic coupling. Yet buried in the supplementary material, a single chart told the real story. Two identical waveforms, one inverted, separated by 9,200 kilometers, and by nothing at all. Whether the cause was electromagnetic resonance, gravitational harmonics, or sheer cosmic accident, one truth lingered. Something had connected Tonga and Chile that day. Two trenches, two hemispheres, one rhythm. And perhaps, just perhaps, it wasn't coincidence at all, but the Earth responding to a distant pulse, a vibration that began not beneath our feet, but out among the stars. Atmospheric, ionospheric disturbances and volcanic coupling. Before any tremor is felt in stone, the air above it often shivers first. Long before the ground beneath Tonga or Chile began to resonate in July 2025, faint atmospheric waves were already moving across the Pacific, invisible ripples in pressure and plasma, caught only by the most sensitive instruments. It was as though the planet itself inhaled before the deep exhale below. When 3I Atlas crossed the sun's meridian, Earth's upper atmosphere was serene by all human measures. No major solar storms, no auroras, no visible sky glow. Yet satellites monitoring the ionosphere, the charged layer 100 kilometers above our heads, began to pick up something peculiar. The total electron content, TEC, values across the Pacific started oscillating in slow, rhythmic intervals. Normally, these oscillations are caused by solar radiation flux or tidal heating. But these waves were different. They formed a geometric interference pattern, stretching from Polynesia to South America like an invisible fingerprint. The frequency of the oscillation, 3.6 minutes per cycle, matched the same deep resonance seen in the Tonga and Chile tremors. That alone might have been coincidence. But when researchers compared the amplitude spikes to solar data, they found no correlating flare, no CME, no geomagnetic storm. Something else had modulated the ionosphere, something local, or perhaps something global but subtle. The Tonga region, though remote, has been a laboratory for atmospheric coupling ever since the cataclysmic eruption of Tonga Ha'apai in 2022. That explosion sent atmospheric pressure waves around the world multiple times, shaking the ionosphere and producing electrical surges detectable as far away as Europe. Scientists discovered that the atmosphere and ionosphere act as mirrors, bouncing energy back and forth between them. A single event in the ocean can reverberate around the entire planet's electrical shell. When the deep harmonic tremors began in July 2025, instruments positioned around the former Tonga site detected faint infrasound bursts, ultra-low pressure waves inaudible to humans but measurable in microbars. The pattern was precise, a repeating series of pulses that intensified during the same hours as the ionospheric oscillations above. To many researchers, this looked like atmospheric to seismic coupling, energy flowing both upward and downward. The mechanism is complex but increasingly recognized. Fluctuations in the ionosphere's electric field can alter atmospheric conductivity, generating vertical currents that travel downward through the air column. When these currents reach the ocean surface, they can influence microbubbles, vapor content, even sea air charge gradients. Over time, those fluctuations can transfer minute stresses to the ocean floor, especially in regions already under tectonic tension. Conversely, when tremors occur deep below, they send acoustic gravity waves upward, slow, rising pressure oscillations that can disturb the ionosphere. This two-way dialogue between Earth and sky is what some scientists now call the lithosphere-atmosphere-ionosphere coupling, LAC system. It's a feedback loop of charge, pressure, and motion, one capable of amplifying signals across domains. During the days of the 3I Atlas alignment, lakes seemed to come alive. The ionospheric anomalies weren't confined to Tonga and Chile. Similar perturbations appeared in satellite tracks over the Central Pacific and the South Atlantic anomaly, a region where Earth's magnetic field is weakest. There, instruments registered irregular bursts of plasma density, rising and falling in tandem with Earth's Schumann resonances, the natural electromagnetic heartbeat of the planet. It was as if the entire atmospheric shell had begun to oscillate in sympathy. Ground stations in Fiji and Tahiti noted short-lived disturbances in radio propagation. Very low frequency, VLF, signals from naval transmitters fluctuated, suggesting sudden changes in ionospheric reflection height. One signal path between Hawaii and New Zealand, usually stable, showed 0.4 Hz modulation, exactly matching the period of the deep Earth tremors. In isolation, each of these anomalies might have been dismissed, but their synchronicity pointed to a shared cause, possibly electromagnetic resonance excited by solar or cosmic influence. The timing again overlapped perfectly with 3 Atlas's solar alignment. Then came the strangest observation. A thermal imaging satellite used for weather monitoring detected transient hotspots on the ocean surface near Tonga, patches less than a kilometer wide, warming by 0.33 degrees Celsius for just minutes at a time. The locations aligned with known hydrothermal vent systems. Scientists speculated that the deep tremors could have temporarily increased vent output, releasing heat plumes that reached the surface. But the timing corresponded, again, to fluctuations in ionospheric activity. Could electromagnetic disturbances above have influenced volcanic systems below? It sounds improbable, yet history gives examples. In 2018, before the Anak Krakatau eruption in Indonesia, satellite data showed strong ionospheric perturbations above the site days earlier. In 2022, during Tonga's explosion, scientists recorded the largest ionospheric disturbance ever observed, a ripple expanding across half the planet. The physics behind this coupling are slowly coming into focus. Changes in electric field potential across the ionosphere can induce telluric currents through conductive pathways, and volcanic systems filled with fluids and metals are particularly sensitive. When those currents pass through hydrothermal regions, they can destabilize fluid pressures or gas solubility, subtly increasing the likelihood of venting or microexplosions. This might explain why Tonga's vent fields showed brief warming after the alignment. Not enough for an eruption, but enough to suggest agitation. In Chile, similar though smaller temperature fluctuations were noted along the submarine volcanic arc west of Valparaiso. Gas emissions from nearby vents showed slight upticks in methane and carbon dioxide, consistent with pressure release. Once again, these anomalies coincided with the same ionospheric oscillations. One particularly telling piece of evidence came from NASA's GOLD, global-scale observations of the Limb and Disk satellite, which images Earth's upper atmosphere. On July 3rd, it captured faint auroral-like emissions near the equator. Red and green glows at 135.6 nanometers, typical of oxygen excitation. These emissions shouldn't appear there. They require energy inputs from space weather or unusual ionospheric heating. No solar flare was recorded, but the emissions appeared precisely above the Tonga-Chile longitude corridor. To space weather analysts, it was a clue that something external, perhaps a transient burst in the interplanetary magnetic field, had briefly energized the upper atmosphere. Whether that energy originated from the sun itself or from the interaction of 3I/Atlas's plasma tail with the solar current sheet, no one could say. But whatever its source, it seemed to trigger a chain reaction extending from 100 kilometers above to 600 kilometers below. It's worth noting that these phenomena occur at vastly different timescales. Ionospheres react within seconds. Magma systems evolve over centuries. Yet the coupling may happen through intermediaries, like the atmosphere's electrical circuit. Between the ionosphere and the Earth's surface flows a continuous vertical current of about 1 to 2 picoamperes per square meter. Disturb that circuit and you change the global electric potential. Even minor modulations can influence lightning rates, cloud ionization, and ultimately the pressure dynamics above active volcanic zones. During the week following 3I/Atlas's Meridian crossing, lightning frequency across the western Pacific increased by 18%, despite stable weather conditions. The strikes clustered along the Tonga-Samoa corridor. To meteorologists, it was anomalous. To space weather observers, it looked like the electrical system of the atmosphere briefly overcharged. Could that energy have found a pathway downward, into the crust, into magma conduits, into fault lines already quivering from deep tremors? If the LAIC mechanism is real, the answer is yes. The process would unfold like this. A change in solar or cosmic electromagnetic conditions alters the ionosphere's charge density. That modifies atmospheric currents, which in turn affect ground potential. Conductive regions, especially near volcanic arcs, experience induced currents that alter pressure and temperature gradients in fluid-filled rocks. Those changes manifest as tremors, venting, or even eruptions. It's a delicate dance between fire and air, and on that July week, every step seemed to match the rhythm of an unseen drummer. By the end of the alignment period, the anomalies faded. The ionosphere stabilized, lightning returned to normal, and the ocean cooled. But when researchers reviewed the data weeks later, they found one final surprise. The residual electromagnetic oscillations, those low-frequency hums first detected in the ionosphere, persisted faintly for days after 3I/Atlas departed. It was as though the atmosphere continued to ring long after the cosmic note had been struck. In that lingering resonance lies the most unsettling implication. If an event as fleeting as an interstellar alignment can imprint measurable signatures in both the ionosphere and the volcanic crust, then the boundary between space and Earth isn't a barrier at all. It's a membrane. A living, vibrating interface where cosmic and terrestrial energies meet and occasionally, under just the right geometry, exchange whispers. Maybe that's all this was, a whisper between the stars and the stone. A moment when the upper air glowed, the deep sea warmed, and the Earth itself seemed to hum in answer to something passing through the solar wind. Or perhaps it was a reminder that what we call empty space is never truly empty, and that sometimes even the most distant traveler can touch the heart of a world. Precursor anomalies, signals before earthquakes. Every major earthquake, no matter how sudden it appears, leaves behind whispers, faint electromagnetic murmurs, atmospheric pulses, and ground vibrations too subtle for humans to notice. For decades, scientists have chased these elusive precursors, hoping to predict quakes before they strike. Most attempts ended in frustration. Too many false positives, too much background noise. Yet, during the strange week of July 2025, as 3I/Atlas aligned with the sun and deep tremors rippled across the Pacific, those same elusive signals began to appear again, only this time they didn't precede destruction. They accompanied resonance. The earliest hints emerged days before the alignment. Ionospheric stations in Tonga, Samoa, and Tahiti recorded unusual fluctuations in total electron content, minor, periodic oscillations that didn't match diurnal solar activity. Normally, tech anomalies occur hours before strong quakes, caused by rising electric fields and changes in atmospheric conductivity above stressed crust. But there was no major earthquake coming. Instead, the signals appeared globally coherent, a soft global hum rather than a localized warning. At 3 UTC on July 1st, Doppler shifts in radio transmissions from Japan's GeoNet system began fluctuating irregularly. The variations were small but unmistakable, the kind of drift typically seen before seismic activity. By noon, the same Doppler noise was detected in the South Pacific region. Researchers at the University of Tokyo, who specialize in electromagnetic precursors, noted that the frequency patterns matched a seismo-ionospheric coupling signature, yet they couldn't assign a location. The anomaly wasn't centered on one fault or trench. It spread evenly across latitudes from Tonga to Chile. Beneath the ocean floor, ultra-deep seismometers began recording sub-audible microquakes, vibrations of such low amplitude they would normally vanish in ambient noise. When those waveforms were filtered and plotted, a pattern emerged. A build-up phase, a plateau, and a decay, repeating roughly every 7 minutes. It was as if the planet's crust was being struck by an unseen drumbeat. Many scientists have long argued that earthquakes are preceded by piezoelectric effects, electrical charges generated as stressed rocks deform. These charges can ionize surrounding air, alter conductivity, and even produce localized electromagnetic emissions known as seismo-EM signals. In the 1980s, Soviet satellites reportedly observed infrared glows over seismic zones days before quakes. Later, NASA's Demeter satellite confirmed similar emissions linked to earthquakes in Japan and Greece. The Tonga-Chile corridor in July 2025 exhibited these same infrared glows, but again without any destructive quake to explain them. Infrared sensors aboard the Suomi NPP satellite showed faint hotspots along the Tonga Trench and off Chile's coast, each roughly 0.2 degrees Celsius warmer than the surrounding ocean surface, appearing and fading over 30-minute windows. They formed a chain-like pattern aligned with Earth's magnetic field lines, the same meridian along which 3I's atlas crossed the sun. The implication was bizarre, a global-scale precursor pattern without a quake, like a warning signal triggered but never delivered. The anomalies didn't stop there. Ground-based magnetometers in Tahiti and Easter Island recorded ultra-low frequency ULF magnetic pulses with amplitudes of 0.1 to 0.3 nanoquint, weak but distinct from background noise. ULF signals are one of the most debated earthquake precursors. They often appear hours or days before significant seismic events. What made these unique was their perfect synchronicity across hemispheres. No known local source could produce simultaneous pulses separated by thousands of kilometers. Could they have originated from space weather? Not likely. The solar flux was steady, and there were no recorded coronal mass ejections or solar flares. Yet the signals had a rhythmic structure, mirroring the same 7-minute periodicity seen in the deep tremors and atmospheric oscillations. It seemed as if the entire Sun-Earth system was vibrating to one frequency, a cosmic resonance bridging plasma, air, and stone. Then came the strangest report of all. A Japanese research satellite measuring very low frequency VLF radio propagation recorded faint bursts of radiation over the Pacific, centered on 19 kilohertz. Normally, these signals are used to detect lightning or auroral activity, but these bursts occurred under clear skies. Their spectral characteristics matched those observed during the early stages of seismic preparation zones, where stressed rocks emit VLF waves as they fracture microscopically. But this was happening in open ocean, over areas of deep subduction where no quakes occurred. A small group of researchers at the Finnish Meteorological Institute began analyzing global Schumann resonance data, the natural electromagnetic oscillation between Earth's surface and ionosphere. They found subtle amplitude modulations during the alignment period. The fundamental frequency, 7.83 Hz, wavered by less than 0.01 Hz, a minute change, but globally coherent. Such modulations have been observed before major earthquakes, believed to reflect shifts in atmospheric ionization. The July anomalies mirrored those same seismic precursors, but on a planetary scale. It was as though the Earth prepared for an earthquake that never came. Geophysicists debated furiously. Some suggested that 3 Atlas's passage through the Sun's magnetic equator might have emitted a pulse of charged plasma that reached Earth, mimicking the electrical environment of a quake zone. Others proposed that deep stress redistribution in the Tonga and Chile slabs temporarily primed the crust, producing precursor-like signals without releasing energy as a surface quake. Either way, the precursors were real. Electromagnetic fingerprints left in the air, sea, and stone. Among the most mysterious were luminous phenomena observed over the South Pacific during the alignment window. Airline pilots flying routes between Sydney and Santiago reported faint blue glows over the ocean, diffuse circular patches that lasted seconds. These weren't sprites or lightning, they were steady glows. Similar earthquake lights have been documented for centuries, atmospheric luminescence caused by electrical discharges from stressed rocks. But again, no major seismic rupture followed. It was as though the crust had charged and discharged invisibly. Laboratory experiments lend some support to this. When granite is compressed to near failure, it emits bursts of photons and charged particles, a microcosmic version of the luminous phenomena pilots reported. If Tonga's and Chile's slabs were flexing under electromagnetic stress from above, perhaps from the solar current sheet disturbance linked to 3I Atlas, then localized discharges could have occurred without surface breakage. The result would be electromagnetic and optical precursors without a traditional earthquake. The ionosphere responded too. Days before the deep tremors, the Cosmic 2 satellite constellation detected vertical plasma holes, regions of depleted electron density, drifting westward across the equatorial Pacific. These holes are often seen after strong earthquakes, when upward propagating acoustic gravity waves disturb plasma layers. Here, they appeared before any seismic signal. The depletion zones moved along the same longitude that connected Tonga and Chile, the so-called Meridian corridor. If the Earth's crust was truly resonating in response to cosmic or solar forcing, then the planet may have generated a false quake signature, a full suite of precursor phenomena without tectonic rupture. That possibility unsettled the scientific community because it blurred the line between internal and external triggers. Normally, earthquake precursors are localized, a buildup of crustal charge, a flicker in local magnetic fields, an atmospheric anomaly overhead. But the 2025 patterns were globalized. The entire Pacific plate seemed to respond as one coherent system, tuned by a frequency that arrived from space. By the night of July 2nd, the precursors faded as quietly as they came. The ULF pulses diminished, Tech values stabilized, and Doppler drifts returned to baseline. Tonga's harmonic tremors eased, and Chile's mirrored vibrations waned. No major quakes followed, only data scattered across archives and instruments telling a story of tension without release. In the months that followed, a few independent researchers compiled the records into what they called the Phantom Earthquake dataset. Their conclusion was daring, that what humanity witnessed in July 2025 might represent the first global-scale pseudo-seismic resonance, the planet briefly reacting to an extraterrestrial magnetic perturbation, a kind of rehearsal quake. Whether that idea holds truth or imagination, one fact remains. The signatures were indistinguishable from genuine earthquake precursors. The Earth behaved exactly as it does before catastrophe, but no catastrophe came. Perhaps that's the deeper mystery. If a passing interstellar object can stir the same electromagnetic conditions as an impending quake, then maybe our planet's sensitivity extends beyond geology into the realm of the cosmic. Maybe Earth doesn't just quake from within. Maybe sometimes it echoes from without. And on those silent days of 2025, under a calm sun and an alien alignment, it seems Earth heard something, a frequency so low and so deep that even without a fracture, it trembled ever so slightly, as though bracing for a voice still traveling toward it from the stars. Statistical evidence, solar seismic correlation. For centuries, the idea that the sun could influence earthquakes lingered in myth and in superstition, a poetic notion whispered in old journals and dismissed by modern geophysics. Yet, in the quiet data archives of space weather observatories, a subtle pattern has begun to emerge. The numbers don't scream, they whisper, and the whisper says, maybe the ancients were right. The sun and Earth are bound by more than light. Every 11 years, the sun's magnetic field flips, its poles exchanging places like celestial lungs exhaling. These reversals drive the solar cycle, peaks and valleys of flares, sunspots, and coronal mass ejections, CMEs. Most effects are confined to the magnetosphere, auroras, radio disruptions, satellite anomalies. But when the cycles are mapped against global earthquake catalogs, coincidences begin to form lines. In 2025, as 3I Atlas crossed the sun's meridian, those lines grew bolder. Researchers at the Geophysical Institute in Prague had long compiled a database of seismic events correlated with solar indices: sunspot number, proton flux, geomagnetic KP index, and the DST index measuring magnetospheric storms. Their dataset, spanning from 1900 to 2024, included over 2 million recorded earthquakes above magnitude 4.0. When plotted against solar activity, small but persistent periodicities appeared. Earthquakes tended to cluster within 10 days of major solar events. Statistically, it shouldn't happen. Yet it did. A 2023 study published in Geosciences refined the method further, using epoch superposition to align 40 years of seismic records with solar flares. The result, a 33% increase in global seismicity following X-class flares in the hemisphere directly facing the sun. The effect vanished when the same data were randomized, proof that the correlation wasn't a coincidence of chance, but of timing. Critics argued the sample was biased, but another independent analysis, using magnetospheric energy flux rather than sunspot counts, confirmed a similar trend. The Earth shook more often after geomagnetic disturbances. The mechanism was unclear, yet the statistical trace persisted. When the July 2025 alignment occurred, data analysts revisited those correlations, now with unprecedented precision. For the first time, multiple planetary scale sensors were monitoring both the Sun and Earth simultaneously. Parker Solar Probe near the Sun, DSCOVR and ACE at L1, and hundreds of ground-based magnetometers ringing the globe. The setup was perfect, a cosmic experiment waiting to happen. On July 2nd, during 3 Atlas's crossing of the solar meridian, the Sun's proton density fluctuated by 6%. That is a small number, almost noise, but statistically significant in an otherwise quiet week. The KP index rose from 1 to 3, the DST index dipped to -14 NTL, and the AE index, measuring auroral electrojet intensity, spiked briefly. Each of these indicators marks small geomagnetic agitation. Within 24 hours, seismographs worldwide registered a 12% increase in microseismic activity. Most were imperceptible, magnitudes between 2.0 and 3.0, but the pattern was global, not local. The largest clustering occurred along subduction arcs: Tonga, Chile, Japan, and the Aleutians. The alignment between solar fluctuation and tectonic hum was uncanny. To test the correlation, a team at the Max Planck Institute for Solar System Research performed a statistical lag analysis. They overlaid 30 years of DST and seismic data, sliding one dataset against the other in 24-hour increments. The peak correlation appeared at plus 1.5 days, meaning earthquakes were most likely to follow geomagnetic dips by roughly 36 hours. Tonga's deep tremors and Chile's mirrored oscillations occurred within that exact window. Coincidence? Possibly. But the historical data echoed the same delay. The Carrington event of 1859, the greatest solar storm ever recorded, was followed by a measurable uptick in seismicity during the following week. The same pattern appeared after the geomagnetic storm of May 1921, and again in March 1989, the storm that shut down Quebec's power grid. None caused immediate global catastrophe, but the Earth's crust seemed to listen, responding faintly to the sun's magnetic breath. To understand why, one must look beneath statistics into the physics of induction. When charged particles from the sun strike Earth's magnetosphere, they compress its field, altering currents in the ionosphere. Those currents, in turn, induce telluric flows within the crust, tiny electrical currents that move through rock and water. Under normal conditions, they're harmless, but when the crust is already near failure, even a minor perturbation can alter local stress fields. It's not unlike plucking a guitar string already stretched to breaking. The added vibration doesn't create tension, it releases it. A 2018 study in Nature Scientific Reports found that earthquakes occurring within 10 days of major geomagnetic storms were 20% more likely to exceed magnitude 6.0. The correlation strengthened near tectonic boundaries rich in conductive minerals, such as subduction zones. Tonga and Chile sit atop precisely such structures. When the July 2025 tremors occurred, both regions were already primed. Tonga by dehydration reactions deep in the slab, Chile by fluid migration in its lower mantle. All they needed was a trigger. The solar alignment provided one. Still, correlation does not prove causation, the golden rule of science. Yet correlations, when layered across decades, begin to whisper of hidden connections. and the whispers are growing louder. The most compelling evidence comes from global geomagnetic storm databases cross-referenced with the United States Geological Survey, USGS, earthquake catalog. When plotted across 40 years, the curves rise and fall together in eerie synchrony. Peaks in geomagnetic activity tend to precede seismic clusters by 1 to 3 days. Some researchers call this phase locking, the idea that two natural oscillators, the sun's magnetic field and Earth's tectonic cycles, can temporarily synchronize. The sun's pulse modulates the magnetosphere modulates the crust. Energy doesn't need to be massive, only timed perfectly. That timing is where 3I Atlas enters the story. Its crossing through the sun's current sheet coincided almost exactly with a geomagnetic dip on Earth. For a few hours, the heliospheric current aligned with Earth's field geometry, tightening magnetic linkage across astronomical space. Statistically, such alignments are rare, less than once per decade. Yet when they occur, the odds of global magnetic perturbation rise sharply. In essence, the 2025 event was a natural laboratory, a near-perfect alignment of solar, interstellar, and terrestrial systems. What followed, synchronized tremors, harmonic oscillations, ionospheric disturbances, mirrored every hallmark of known solar seismic correlations, but magnified. If the correlation is real, what does it mean for prediction? Statistical models are improving. Using machine learning trained on decades of solar and seismic data, a few experimental systems have begun to forecast increased seismic probability following specific space weather conditions. Southward IMF, interplanetary magnetic field, rapid solar wind shifts, and high-density plasma streams. The model used for 2025 flagged the period around July 2nd as moderate geomagnetic risk. It wasn't predicting quakes, it was predicting instability. Afterward, the validation metrics shocked even skeptics. The model's confidence scores spiked precisely when Tonga's deep tremors began. In retrospect, it looked prophetic, though it had no way of knowing that an interstellar object would cross the sun's meridian at the same moment. And so, a new question emerged. Did 3 Atlas simply coincide with a natural solar pulse, or did its passage enhance it? Some plasma physicists suspect that interstellar objects coated with ionized gases can temporarily distort the heliospheric current sheet as they pass through it. That distortion might focus magnetic energy towards certain sectors of the sun, subtly amplifying output along specific longitudes, like a lens bending sunlight. If Earth happened to be on that longitude, it could experience a brief but measurable surge in magnetic forcing. Statistically, such coincidences are nearly impossible, unless the cosmos itself has patterns we've yet to perceive. By late 2025, review panels re-examining the event noted something else. Seismic activity globally decreased after July, following the brief spike. It was as though the planet had discharged built-up tension in harmless tremors, a safety valve released by solar rhythm. The correlation curve inverted, a rise followed by a long calm. The Earth, it seems, may not simply react to the sun's fury. It may synchronize with it, tuning its cycles of release and rest to solar rhythm. That idea, solar tectonic synchrony, is gaining traction in some circles. Others call it pseudoscience. But the data stubbornly remain. The sun flares, the magnetosphere ripples. Hours later, the deep Earth stirs. Across a century of measurements, through different cycles and instruments, that rhythm endures, faint but persistent. And when 3I Atlas passed across the sun's face, that rhythm seemed to crescendo for just a moment into something unmistakable, a statistical ghost becoming physical reality. Perhaps the ancients who spoke of the sun as the heart of the Earth weren't entirely wrong. Perhaps every tremor is, in some infinitesimal way, a heartbeat, not just of our planet, but of the star that gave it life. And if that's true, then 3I Atlas didn't cause the tremors. It simply passed through a living system already pulsing, and for one brief instant, everything resonated in unison. Coincidences stacking, multiple alignments. At first glance, the July 2025 alignment of 3 Atlas with the sun's meridian seemed extraordinary enough. But as researchers began to layer event after event, solar, magnetic, seismic, atmospheric, the coincidences started stacking like cosmic dominoes. Each might be dismissed in isolation. Together, they formed a geometry too precise, too recursive, too synchronized to ignore. On the surface, it began with a simple three-body line: sun, interstellar object, Earth. Yet, as the alignment unfolded, the rest of the solar system appeared to respond in subtle ways. Venus was approaching inferior conjunction, Mercury had just passed perihelion, and Earth's magnetosphere was positioned almost edge-on to the interplanetary magnetic field. To anyone studying celestial mechanics, it was an odd configuration, a cascade of near symmetries, as if the solar system had momentarily tuned itself into resonance. That word, resonance, became the center of the investigation, because by the time 3I Atlas had crossed the solar meridian, resonance wasn't just metaphorical, it was measurable. In those same hours, the sun's global oscillation data, collected from helioseismology instruments on NASA's Solar Dynamics Observatory, showed faint perturbations in its 5-minute oscillation mode. The sun vibrates continuously, its surface rippling like a drum under magnetic tension. But on July 2nd, one frequency band, 3.5 MHz, showed an anomaly, a sustained amplitude increase lasting nearly 2 hours. It was small, but statistically significant. 2 hours later, Earth's Schumann resonance, the global electromagnetic hum generated by lightning between surface and ionosphere, spiked by an identical fraction. The temporal separation matched the travel time of the solar wind between the sun and Earth. Coincidence? Perhaps. But the alignment deepened. Jupiter's magnetosphere, the largest magnetic structure in the solar system, experienced a minor radio burst recorded by the Juno spacecraft, a narrow-band emission around 10 MHz. No preceding solar flare or CME was observed. And yet, the emission occurred at the precise moment 3I Atlas crossed the sun's equatorial current sheet, the same magnetic plane connecting the sun, Earth, and Jupiter at that instant. It was as though the entire heliosphere had felt the crossing, like a plucked string resonating from one end to another. The geometry of this event was uncanny. When scientists reconstructed the alignment in heliographic coordinates, the line connecting 3I Atlas, the sun, and Earth intersected not just our planet, but the Pacific Basin, directly between Tonga and Chile, the same corridor where harmonic tremors and ionospheric anomalies had manifested. The spatial overlay was almost perfect. One physicist, Dr. Enrico Vallis from the European Space Agency, put it bluntly during an internal briefing. Open quote, "We are either witnessing one of the most elaborate coincidences in heliophysics history, or we are looking at a resonance chain that connects celestial geometry with geophysical activity." Close quote, the phrase resonance chain quickly spread through the research community. When geomagnetic data from the week were plotted across the globe, the disturbances weren't random. Instead, they formed nodal regions along specific longitudes: the Pacific Trench Arc, the Andes, and the Arctic cusp. The pattern mirrored standing wave modes known to occur during planetary alignments, when gravitational tides subtly modulate the magnetosphere's shape. These waves can reinforce or cancel each other, and in 2025 they reinforced. But the coincidences didn't stop at the planetary scale. At the same time, the moon was nearing its apogee, its farthest distance from Earth, meaning its gravitational influence was minimal. Tidal forces, often cited to explain simultaneous seismic events, were at their weakest. This removed one of the most common coincidence explanations. The tremors beneath Tonga and Chile couldn't have been driven by the moon, yet both occurred precisely during geomagnetic maxima induced by the solar alignment. Adding to the mystery, on July 1st, just 24 hours before the crossing, NASA's Parker Solar Probe detected a faint structured plasma oscillation near perihelion, a signal oscillating every 420 seconds, identical to the frequency detected by ground-based magnetometers a day later. Plasma physicists initially labeled it a data artifact. Then a similar periodicity appeared in Earth's magnetotail on July 3rd, recorded by the Themis satellites. The phase difference matched the propagation time of solar wind disturbances from Parker's position to Earth. So the chain was complete: solar oscillation, plasma wave, magnetospheric resonance, seismic tremor. Even if each link was weak, together they formed a coherent timing pattern. By July 5th, public space weather dashboards showed no dramatic activity. The world had gone on unaware. But in small corners of the scientific internet, plots were circulating, overlays of cosmic geometry and planetary data. When heliophysicists extended the alignment lines outward, something startling appeared. Mars, too, was nearly collinear, though offset by several degrees. And just behind Mars, the trajectory of comet P 2025 H3, a long-period visitor, intersected the same heliographic longitude. Two solar crossing bodies, one interstellar and one native, both aligned with Earth across the same meridian within days. What were the odds? Astronomers calculated them, roughly 1 in 2.4 million. At the same time, a completely separate anomaly was reported by NASA's Deep Space Network. Minor signal interference affecting spacecraft telemetry across multiple antennas. The interference lasted only minutes, but its spectral pattern resembled a low-frequency plasma fluctuation, the same type of event capable of modulating radio propagation through the solar wind. It coincided perfectly with the alignment's midpoint, coincidences stacking one atop another. Still, science demands skepticism. The human mind sees patterns where none exist. Could this simply be confirmation bias? To test that, analysts compared the event with other alignments. For example, when Oumuamua, the first interstellar object, passed near the Sun in 2017. Despite similar geometry, no global seismic or magnetic disturbances occurred. But crucial differences stood out. Oumuamua crossed during high solar activity when the magnetosphere was already turbulent. 3I Atlas, by contrast, passed during a lull, the calm between flares, a silence where any small perturbation would stand out clearly. The context, in other words, made this alignment uniquely visible. Meanwhile, new coincidences continued to unfold. Satellite gravimeters detected minute variations in Earth's gravity field during the week, on the order of microgals, too small for ordinary geophysical sources. These fluctuations matched the Pacific longitudes already implicated in the tremors, whether caused by density changes in the atmosphere or transient shifts in Earth's core mantle boundary, no one could say. Then came one of the strangest correlations of all. On July 2nd, observatories in Hawaii and Chile reported faint increases in cosmic ray muon counts, particles that constantly rain through Earth's atmosphere. Normally, muon flux fluctuates with solar magnetic shielding. When the sun's field strengthens, fewer cosmic rays reach Earth. During the alignment, muon rates rose sharply, suggesting a temporary weakening of the solar shield. That implies something in the heliosphere, perhaps 3I Atlas itself, disturbed the normal flow of magnetic deflection, allowing a brief increase in cosmic radiation. Muons can penetrate deep underground, affecting detectors and even, theoretically, influencing geophysical chemistry. If the cosmic ray spike was real, it could have subtly altered charge distribution across the crust, priming conductive regions for resonance. By now, the word coincidence had lost its comfort. Across data centers, scientists began layering datasets, solar, seismic, atmospheric, ionospheric, and finding one unifying timestamp, July 2nd, 2025, between 11 and 15 UTC. No matter the instrument or domain, some form of anomaly registered during those 4 hours. And then, as if to mock the skeptics, the cosmos offered another alignment, a literal echo. On the opposite side of the Sun, the comet Encke was simultaneously crossing its own perihelion, forming a secondary line nearly 180 degrees from 3 atlases. The two paths were mirror-symmetric through the Sun. In celestial geometry, that configuration is called antipodal alignment, exceedingly rare, almost never involving active bodies. For 4 hours, the solar system's architecture resembled a tuning fork, two interstellar and interplanetary masses oscillating across the Sun, their fields slicing through the same heliospheric sheet from opposite directions. The physics of this symmetry are staggering. The heliosphere's magnetic current sheet undulates like a ribbon. When two conductive objects pass through it from opposite sides, they can, in theory, produce a standing wave, a resonant vibration across the Sun's magnetic field. If such a wave existed, its frequency would match the periodicity observed in Earth's magnetosphere that day. It was as if the entire solar system had momentarily sung a note, and Earth, suspended within its resonance, trembled softly in reply. Even among skeptics, the stacking coincidences became impossible to ignore. One astrophysicist summed it up during a quiet interview, open quote, "Science doesn't like coincidences in threes. We now have a dozen," close quote. And yet, in the official archives, the event remains classified as unremarkable. No significant solar storm, no recorded seismic crisis. But beneath that sterile summary lies a deeper pattern, a whisper of synchronization between worlds. 3I Atlas, the Sun's Meridian, Earth's trembling crust, the alignment of planets, the echo of comets, the pulse of magnetospheres. Coincidence? Yes. Stacked upon coincidence until the boundary between chance and choreography dissolves. Perhaps that's the true story of July 2025. Not that something caused anything, but that everything, for one brief instant, aligned too perfectly to feel random. And somewhere in that fragile symmetry between geometry and gravity, between plasma and stone, the universe revealed what it always hides behind statistics. That pattern itself might be its language, and resonance its only truth. Mechanisms. How might space weather affect deep Earth? For most of scientific history, the boundaries between the sun and the solid Earth have been treated as separate kingdoms, one of plasma, one of stone. Space weather belongs to the stars, earthquakes belong to the crust. Yet time and again, subtle signals blur that line. When geomagnetic storms pass, compasses twitch, pipelines spark, power grids overload, and occasionally the Earth's deep layers stir in sympathy. The mechanism, if it exists, has never been fully defined. But July 2025, when 3I Atlas crossed the sun's meridian and the planet seemed to hum, forced researchers to reconsider. How could electromagnetic storms in space reach 600 kilometers down into rock? It begins with induction. Every conductive medium, wire, seawater, or slab of basalt, responds to changing magnetic fields. When the solar wind buffets Earth's magnetosphere, it distorts that field, generating electrical currents known as geomagnetically induced currents, GICs. At the surface, GICs flow through power lines and pipelines, but they also run silently through the crust and mantle, following veins of ore, groundwater, and molten rock. The physics is simple. Faraday's law in action: a moving magnetic field creates electric current. The mystery lies in scale. During a major geomagnetic storm, potential differences of several volts per kilometer can develop in Earth's surface layers. That might sound small, but over a tectonic fault stretching hundreds of kilometers, the energy becomes enormous, comparable to the charge stored in a thundercloud, but buried beneath our feet. These telluric currents preferentially flow along boundaries between wet and dry rock, or conductive and resistive zones. Coincidentally, these are the same boundaries where earthquakes nucleate. Researchers studying Japan's Nankai Trough have shown that during solar storms, the conductivity of the crust can change measurably, as if the rocks themselves were breathing with the magnetic field. Minerals like magnetite and pyrrhotite act as microscopic transducers, converting magnetic oscillations into mechanical stress. Over years, these invisible pulses might fatigue rocks, subtly altering the timing of their rupture. That's one route, electromagnetic induction as a geological catalyst. But others are more exotic. The second mechanism involves piezoelectric coupling. Quartz, one of the most abundant minerals in continental crust, generates voltage when compressed. If deep stressed rock already carries charge, an external electromagnetic field can interact with it, changing local stress distributions. Laboratory experiments at the University of Kyoto showed that applying oscillating magnetic fields to compressed granite blocks increased microfracturing rates by up to 15%. In other words, electromagnetic fields can tickle stressed rock to releasing energy sooner. Now scale that experiment up to the size of a tectonic plate. During strong space weather events, oscillating magnetic fields sweep across the planet, inducing transient electric currents that could interact with naturally charged faults. In regions like Tonga or Chile, where immense slabs grind under enormous pressure, that additional modulation could act as a trigger, the final nudge. But to reach deep Earth, hundreds of kilometers down, electromagnetic effects face another problem: attenuation. Rocks are resistive. Currents weaken quickly with depth. How then could space weather reach the mantle? This question divides the field. Some insist it can't. The energy dissipates within tens of kilometers. Others propose that the coupling doesn't rely on direct current flow, but on wave resonance. Here's how that might work. Earth's magnetic field lines form a gigantic resonant cavity with the solar wind. When plasma waves ripple through this cavity, for instance during a coronal mass ejection, they generate ultra-low frequency ULF electromagnetic oscillations. These ULF waves, typically 0.01101 Hz, match the natural frequencies of many geophysical processes: ocean tides, atmospheric oscillations, even deep Earth free oscillations. In other words, the same frequencies that shake the magnetosphere can resonate with the solid planet. Simulations by the Finnish Meteorological Institute show that ULF waves can penetrate several hundred kilometers into Earth's crust, especially along conductive pathways like oceanic subduction zones. Once there, the oscillations can alter stress rates cyclically, minuscule but perhaps sufficient to synchronize microslips or fluid migration in fault zones. The Tonga and Chile slabs, soaked with water and minerals, are nearly ideal resonators for such coupling. That brings us to the third, often overlooked mediator: fluids. The crust and mantle aren't static blocks of stone, they are riddled with fluids: brines, molten silicates, carbon dioxide, and water. These fluids respond strongly to electromagnetic fields because they contain ions. When GICs or ULF waves pass through them, they can induce electroosmotic flow, the migration of charged fluids along grain boundaries. This effect, though tiny on human scales, could alter pore pressure over kilometers, changing how stress accumulates and releases. In 2014, researchers studying geothermal systems in Iceland found that groundwater pressure fluctuated with geomagnetic activity. The variations followed KP index values, higher during magnetic storms, lower during quiet periods. The mechanism: induced currents changing electrochemical gradients underground. If that happens in shallow aquifers, why not in the mantle wedge above subduction zones, where fluids lubricate slab movement? A minor modulation there could cascade into larger mechanical effects. Fourth, thermal coupling. The ionosphere and atmosphere heat during geomagnetic disturbances, expanding slightly. This expansion changes air pressure, which transmits to the surface as acoustic gravity waves, slow, deep-reaching oscillations that can affect the ocean and crust. The Hunga Tonga eruption of 2022 proved how powerful this pathway can be. Its shockwave traveled around the world multiple times, coupling atmosphere to ionosphere and back. The reverse process, from above downward, is less violent but constant. During solar storms, pressure anomalies ripple downward, generating microstrain in the crust. When 3I Atlas aligned in July 2025, similar oscillations were detected, faint but planetary. A fifth and still more speculative mechanism involves particle penetration. During intense magnetic disturbances, energetic particles, protons and electrons, can enter the atmosphere, increasing ionization and secondary radiation, muons. These particles can penetrate kilometers underground. Over time, repeated exposure alters the conductivity of subsurface materials, changing how they respond to future storms. It's a slow feedback loop, the crust learning the rhythm of the sun. The deeper mystery, however, lies in synchronization, the way so many systems seem to pulse together during alignments. When the sun's field interacts with Earth's magnetosphere, the whole planet vibrates at multiple harmonics. Schumann resonances in the ionosphere oscillate near 8 Hz. Geomagnetic pulsations range from 0.01 to 5 Hz. Deep Earth-free oscillations occur between 0.001 to 1 Hz. Overlaps between these frequencies create conditions for resonance, where even small inputs amplify dramatically. Imagine the Earth as a drum, the sun as its drummer. Most beats are gentle, lost in the noise of daily geophysical chaos. But occasionally, when geometry, plasma flow, and magnetic orientation align, the beat strikes a resonant note. Energy travels farther, deeper, cleaner. That may have happened during the 3I Atlas alignment. Support for this idea came from Japan's Kagra Gravitational Observatory, which inadvertently detected low-frequency seismic noise during the event. The pattern matched a 0.3 Hz oscillation, identical to a known magnetospheric wave mode recorded simultaneously by the Swarm satellite constellation. One signal in the sky, one underground, vibrating together across 500,000 kilometers of space. This coincidence redefined what scientists meant by coupling. The energy wasn't drilling downward like a current, it was resonating through shared frequency space. If that's true, then depth ceases to be a barrier. The deep mantle doesn't need to be reached directly. It simply needs to be part of the same vibrational network. Just as a bell rings from handle to rim, the Earth may transmit magnetospheric resonance through its whole body, from ionosphere to core. Critics warn against overreach. After all, correlation is not causation. Earthquakes occur daily, solar storms occur daily. Overlap is inevitable. But skeptics face a growing pile of anomalies: synchronized tremors, global electromagnetic oscillations, and ionospheric disturbances that align with cosmic geometry. The data defy easy dismissal. By late 2025, a new interdisciplinary field quietly formed: heliogeodynamics, the study of how solar and interstellar processes might modulate planetary interiors. Its founding principle isn't that the sun causes quakes, but that it can tune the Earth's energy state, just as weather doesn't cause tides, but modulates them. If that's true, then alignments like 3i atlases aren't accidents. They're harmonic events, moments when systems briefly synchronize, revealing their hidden connectedness. From the magnetic ballet in the sky to the deep murmurs beneath the sea, the evidence points to a single, unifying mechanism: resonance through electromagnetism, mediated by the sun's rhythm and magnified by geometry. Perhaps the Earth isn't merely a passive world orbiting its star. Perhaps it's an instrument in a cosmic orchestra, each solar pulse setting off harmonics that travel through crust, mantle, and core. And when a new conductor, an interstellar traveler like 3i Atlas, passes through the orchestra's center, brushing the sun's magnetic strings, even the deepest layers of Earth might feel the faintest vibration. For a moment in July 2025, they did. The instruments trembled, the frequencies aligned, and in the deep silence below, the planet answered, not with catastrophe, but with resonance, proving that even stone can listen to the music of space. Data anomalies and unexplained readings. Every scientific mystery begins the same way, with data that refuses to behave, numbers that don't fit, graphs that refuse to align, readings that mock calibration. July 2025 was full of them. The deeper investigators dug into the records of 3i Atlas's solar meridian crossing, the more the data seemed to slip through their fingers, as if the event itself distorted not just instruments, but the logic that tied those instruments together. The anomalies began quietly. On the morning of July 2nd, multiple magnetometers across the Pacific network began recording what technicians first called phase lag drift. Normally, geomagnetic oscillations across long distances remain in sync within milliseconds. That day, synchronization slipped by nearly 8 seconds between Tonga's and Hawaii's stations. In a system designed to measure nanotesla level changes, an 8-second drift was colossal. When analysts attempted to realign the data using GPS timestamps, they found something stranger. The lag wasn't constant, it oscillated. The delay between instruments waxed and waned every 7 minutes, matching the same periodicity found in deep seismic tremors and Schumann resonance variations. The entire timing network, synchronized through satellite atomic clocks, appeared to pulse, as if the Earth's magnetic shell itself were breathing. Technicians blamed GPS signal noise or temporary satellite desynchronization. But GPS systems are stabilized by multiple atomic clocks in orbit, each cross-checked by ground control. For all to fluctuate in rhythm across half the planet would require a global interference, a perturbation that affected the ionosphere itself, through which all GPS signals pass. Then came the seismograph glitch. At the Tonga Ridge Array, deep sensors registered faint microseismic signals, steady, harmonic, but with one impossible feature: reverse propagation. The waves appeared to originate not from the trench below, but from above, descending through the crust. The pattern inverted the classic P-wave, S-wave arrival times, a phenomenon never observed outside of explosive testing. No volcanic eruption, meteor impact, or detonation occurred in the area. Yet the sensors insisted. The first motion came downward. Across the Pacific, Chile's seismic stations recorded nearly identical reversals hours later. When visualized in waveform software, the two signals mirrored each other like bookends. Tonga's pulse descending, Chile's rising. Analysts could only describe it as phase inversion symmetry, a term borrowed from quantum mechanics rather than seismology. In space weather archives, things were no less peculiar. NASA's ACE spacecraft at the L1 point detected a brief but structured spike in solar wind density, a clean, triangular pulse lasting 14 minutes. The data trace was so geometric that at first it was flagged as software interpolation error. Yet, identical spikes appeared in data from JAXA's Solar B satellite and ESA's cluster mission, each at precisely the same moment. The pulse propagated outward through the heliosphere like a shockwave. No CME, no flare, no coronal hole. Nothing visible on the sun's surface explained it. Parker Solar Probe, closer to the source, captured a plasma wave train crossing its detectors just hours earlier. The waveform resembled a chirp, a rising tone in both frequency and amplitude. It's the same pattern produced when a coherent wave encounters resonance. Some theorists speculated that 3I Atlas, crossing the sun's current sheet, might have acted as a catalyst, generating a magnetoacoustic pulse that raced outward through the solar wind. By the time it reached Earth, it had weakened, but left behind a fingerprint of symmetry in every dataset it touched. The radio domain was equally haunted. Across a dozen observatories, from Canberra to Santiago, astronomers monitoring background cosmic noise noticed a narrowband interference pattern sweeping through their recordings. The frequency drifted downward from 19.3 MHz to 18.7 MHz over a 6-hour period, repeating 3 times before vanishing. It wasn't a known transmission, nor consistent with ionospheric reflection. Even more unsettling, the pattern's drift rate matched the Doppler velocity of 3I Atlas as viewed from Earth. It was as if the object itself was briefly singing across radio frequencies, though no known mechanism could explain how. When cross-correlated with ground magnetometer data, the signal appeared strongest over the Pacific, the same region already exhibiting seismic and atmospheric anomalies. However, attempts to triangulate the source failed. The radio wave direction varied unpredictably, sometimes appearing to originate from the sun, sometimes from the Earth's night side. Data analysts labeled it DRP 725, shorthand for Drifting Radio Phenomenon, July 2, 2025. Unofficially, they called it the Whisper. Around the same time, anomalies began appearing in satellite imagery, faint, halo-like distortions encircling the limb of Earth's atmosphere. The distortions didn't match auroral emissions or airglow. Instead, they appeared as transient opacity bands, bending light differently for just fractions of a second. To optical physicists, the effect looked like rapid variations in atmospheric refractive index, possibly caused by microbursts of ionization. The European Space Agency's MEDOP weather satellites recorded spikes in upper atmospheric NO2 concentration and infrared brightness temperature anomalies across the same longitudes. Again, the effect was too symmetrical to be random, a line of faint heating tracing the subsolar meridian. Something in the atmosphere, the magnetosphere, and the crust was oscillating in unison. Then, on July 3rd, something even stranger happened. The data stopped. For nearly 40 minutes, several Pacific magnetometer stations went offline simultaneously. No hardware failure, no communication loss, just a gap. When the systems came back online, the baseline field intensity had shifted by about 3 NT, small but measurable. The loss window corresponded exactly to the tail end of the 14-minute solar wind pulse observed by ACE. Independent observers found that other datasets also exhibited missing frames during this same window. Oceanic buoy readings, ionospheric tech maps, even certain deep space telemetry streams. It was as if an electromagnetic curtain had briefly swept across the Pacific hemisphere, scrambling sensors and resetting baselines. Data curators called it the gap. When data resumed, certain instruments didn't behave the same. Tonga's seismic stations showed slight phase distortions in subsequent recordings, as if their internal clocks had drifted out of sync. Calibrations fixed the timestamps but couldn't restore waveform fidelity. Even days later, residual ringing remained in the data, a ghost oscillation persisting well beyond the physical event. The same echo haunted magnetometers, a lingering ultra-low frequency wave oscillating around 0.27 Hz, slowly fading over the next 36 hours. When plotted across multiple observatories, that frequency formed a perfect standing wave pattern spanning the Pacific. Node to node, crest to crest, it was the same frequency seen in the deep Earth tremors. Coincidence, or some deeper coupling between magnetic and mechanical oscillations? Other anomalies defied even theoretical framing. A set of gravimetric sensors at the South Pole, used to detect changes in Earth's mass distribution, registered microvariations during the alignment period. The changes were absurdly small, equivalent to 0.1 parts per billion of Earth's gravity field. Yet their timing overlapped precisely with the magnetospheric pulse. To test for instrumental error, data from multiple satellites, Grace-Fo and JOST archives, were cross-compared. Both showed transient microgravity deviations in the Pacific region, synchronized to the Tonga-Chile axis. No geophysical mechanism could explain such instantaneous mass fluctuations. It was as if the planet's density briefly shimmered. Meanwhile, AI systems trained on space weather monitoring flagged the entire event as inconsistent with known solar categories. The algorithm labeled it a Class X0 anomaly, not a flare, not a CME, not a proton event, but something else entirely. When asked to classify it, the system returned a probability map reading 93% unknown transient, 7% composite event. In human terms, it had no match in recorded history. Data from the Japan Meteorological Agency's Ionosan network revealed one last enigma. Just before the alignment peak, vertical electron density profiles over the western Pacific showed inverted layers, a rare condition where upper layers became denser than lower ones. The reversal persisted for nearly an hour, effectively turning the ionosphere into a giant waveguide. During this interval, radio signals traveled unusually far with almost no loss, as if Earth's upper atmosphere had become a mirror for electromagnetic resonance. Could this have amplified the magnetic pulse, feeding back into the planet's crust like an echo chamber? Some researchers think so. In the aftermath, as scientists scrambled to reconcile the chaos, data repositories began showing minor inconsistencies. Files missing timestamps, duplicated records, sensor logs rewritten. Whether due to human error or digital corruption, no one could be sure. But the pattern was too ironic to ignore. The data about the anomalies had itself become anomalous. By August, reports trickled in quietly to national agencies. Each described fragments of the same story: unexplained phase shifts, unexplained ionospheric inversions, unexplained radio patterns. None dared link them to 3I Atlas directly, though the timing made the connection unavoidable. In internal memos, one sentence recurred: correlation without causation, but persistent beyond noise. Perhaps that's the best definition of anomaly there is, a ghost too consistent to be dismissed, too slippery to be caught. Even now, buried deep in archives, the traces remain. A 7-minute heartbeat through the magnetosphere, a 14-minute solar pulse, a 40-minute blackout. Each number a fragment of a pattern that shouldn't exist. The official conclusion, filed months later, was brief: no significant geomagnetic storm. Minor sensor drift observed, but those who stared longest into the data know better. The sensors weren't drifting, the planet was. For one brief moment, Earth's instruments, magnetic, seismic, atmospheric, all fell out of sync together. Not by failure, but by force. And whatever caused it didn't come from the sun or from below, but from somewhere in between, the invisible space where solar wind meets planetary field, and where, perhaps, something from beyond brushed against the currents and left the faintest trace of its passing. Controversies and alternative interpretations. No scientific mystery survives long without a fracture line, a split between those who believe the data point to something extraordinary and those who see only the ordinary wrapped in coincidence. The events surrounding July 2025, when 3I Atlas crossed the sun's meridian and the Pacific trembled in eerie resonance, were no exception. The findings, from synchronized tremors to magnetic pulses and atmospheric inversions, ignited debates that spread from seismological institutes to astrophysics conferences, from underground research circles to late-night television. For every scientist arguing that Earth had experienced a rare instance of solar-terrestrial resonance, another insisted it was little more than a statistical mirage. The skeptics began with the oldest weapon in science, Occam's razor. The simplest explanation, said Dr. Lionel Hartman of the U.S. Geological Survey, is still that subduction zones produce deep tremors, and that global magnetic fluctuations are constant noise. Coincidence is not causation. Correlation without mechanism is mythology. Hartman's critique gained traction. He pointed out that microtremors in Tonga and Chile are nearly continuous. Hundreds occur each month. To link a few hours of harmonic resonance to an interstellar object millions of kilometers away, he argued, was astrological thinking in lab coats. Others agreed, suggesting data cherry-picking and confirmation bias. Every alignment will produce patterns if you look hard enough, said solar physicist Dr. Priya Kandaswamy. The human brain is a pattern machine, but physics doesn't care about our symmetry fetish. Yet not all skeptics dismissed the data outright. Some conceded that the anomalies were real, but argued they stemmed from Earth-based phenomena. One hypothesis proposed that the simultaneous tremors in Tonga and Chile were linked through seismic normal modes, planet-wide vibrations that ring through Earth after major quakes. Such modes can persist for weeks, subtly modulating seismic noise across hemispheres. It's like the planet remembering its last trauma, said geophysicist Alejandro Ruiz. When you listen closely enough, you can hear the echo. Still, no large quake had occurred in the preceding weeks that could explain the precise frequency match between the two regions. Ruiz shrugged, sometimes the Earth improvises. Another camp attributed the data irregularities to instrumentation, the Achilles heel of high-sensitivity science. Magnetometers saturate, seismometers drift, ionosons misfire. A small synchronization glitch in satellite timing, they argued, could produce the illusion of simultaneous resonance. The mysterious phase lag drift between Tonga and Hawaii's sensors might have been no more exotic than a GPS calibration bug. Indeed, the timing networks used in 2025 were under quiet review that summer, following a software update that slightly altered their time integration algorithms. The coincidence between that update and the anomalies fueled fierce backroom arguments. Even so, certain features resisted such mundane dismissal. The phase lag oscillated in regular cycles, precisely 7 minutes apart, long after the timing systems had stabilized. Software doesn't breathe, countered Dr. Mei Lin of the Chinese Academy of Sciences. Something rhythmic was modulating those signals externally. Lin became one of the most prominent defenders of the coupling hypothesis, the idea that the sun's electromagnetic activity can influence tectonic stress indirectly through resonance. She did not claim that 3I Atlas caused earthquakes, only that the object's trajectory intersected the heliospheric current sheet at a moment when Earth's magnetic geometry was unusually receptive. Think of it as plucking a string already under tension, she told Nature Asia. The force is small, but the resonance makes it sing. That word, resonance, became both shield and target. To believers, it explained the patterns too delicate for linear causality. To skeptics, it was a placeholder for ignorance, a poetic synonym for we don't know. The controversy reached its peak when the International Association of Geomagnetism and Aeronomy, IAGA, convened an emergency session in Geneva to review the event. The proceedings were tense. Data from multiple agencies were compared side by side, and the contradictions multiplied. Some magnetometers showed clear 7-minute oscillations, others showed none. Some seismographs displayed harmonic tremors. Neighboring stations remained flat. The inconsistency gave skeptics ammunition. If the effect is global, Hartman quipped, why does it skip half the planet? Proponents countered that resonance doesn't distribute evenly. It amplifies along conductive corridors like oceanic arcs and vanishes in resistive continental crust. It's not a blanket, it's a cord, said Lin. The debates spilled into the public domain. News outlets, hungry for drama, framed the story as a cosmic thriller. Did an interstellar visitor stir the Earth's core? Conspiracy channels spun wilder versions, claiming NASA had cut live feeds during the gap, that data corruption was deliberate, that 3I Atlas was an engineered probe emitting electromagnetic pulses. The real scientists cringed as speculation metastasized. Still, some of those speculations weren't entirely baseless. The official datasets had contained missing timestamps and conflicting readings. Whether due to human error or natural interference, the result was the same: ambiguity. Ambiguity is the death of consensus. Meanwhile, a third faction, the moderates, emerged, seeking compromise. They neither denied the anomalies nor sanctified them. To them, the 2025 event was not proof of cosmic coupling, but a lesson in complexity. Dr. Sandrine Diaye from the CNRS in France described it as a multi-domain resonance cascade, an event where independent systems, solar, atmospheric, seismic, briefly aligned through statistical synchronicity rather than direct causation. The systems are coupled only because they share time, she explained. It's temporal resonance, not energy transfer. This notion that the universe occasionally synchronizes through time rather than force bridged the gap between physics and philosophy. It suggested that 3I Atlas might not have caused anything but merely arrived at a moment when every system, from sun to sea floor, happened to oscillate in phase. To some, that sounded like mysticism. To others, it felt like truth. NASA and SA issued joint statements downplaying extraordinary claims. Their review teams attributed the plasma pulse seen by ACE and Solar B to overlapping data compression artifacts. Not an external event, the report read, but a misalignment between telemetry packages. The explanation was neat, verifiable, and wholly unconvincing to those who'd seen the raw data before it was archived. Independent researchers leaked internal memos showing that the plasma pulse had also been detected by at least one spacecraft not using the same telemetry system, suggesting the artifact explanation couldn't cover all cases. The agencies refused further comment. For months, debates circled like orbits. At the University of Tokyo, graduate students nicknamed the phenomenon the Pacific Echo. They compiled every known anomaly into a single dashboard: tremor waveforms, magnetometer drifts, ionospheric inversions, radio bursts. When plotted against time, the data lined up with eerie precision. Even if it's all coincidence, one student said, "It's the most beautiful coincidence I've ever seen." But beauty has always made scientists uneasy. A small but vocal minority pushed a radical reinterpretation that the anomalies were neither natural nor accidental, but signals from the object itself. What if 3I Atlas isn't a comet? Asked astrophysicist Kaito Sakamura during a symposium in Kyoto. What if it's transmitting, interacting electromagnetically with the sun to announce its presence? The audience laughed, yet his presentation included spectral graphs from radio telescopes showing that drifting frequency between 19.3 and 18.7 megahertz perfectly matched to the object's relative velocity. It wasn't proof, but it wasn't dismissible either. Mainstream astronomers quickly distanced themselves. Interstellar artifact theories belong in science fiction, said Harvard's Dr. Marissa Grant. You can explain every signal as natural once you account for plasma scattering, Doppler smearing, and observer bias. But not everyone agreed. A leaked European Southern Observatory memo revealed internal debates over unusual polarization readings in the object's tail, readings consistent with structured, non-random alignment of particles. If nature made this, one scientist wrote, it's mimicking engineering. By autumn, the academic world fractured into camps. The materialists insisting all anomalies stemmed from terrestrial or instrumental causes. The resonators, arguing for cross-domain solar-terrestrial coupling amplified by 3 Atlas's geometry. The exotics, speculating that the object itself emitted or interacted through unknown physics. None could fully disprove the others. The final conference on the event, held in Reykjavik, ended without consensus. The summary report, delicately worded, captured the mood of exhaustion. Open quote, "The July 2025 anomalies remain unexplained within conventional frameworks. Data inconsistencies preclude definitive attribution. Multiple natural and instrumental causes are plausible. Further monitoring of heliospheric terrestrial interactions is recommended." Close quote. Officially, that was the end. Unofficially, it was only the beginning. Because even after the debates faded, the data refused to. Instruments around the world continue to pick up faint echoes of the July signal, ultra-low frequency waves repeating every 7 minutes, like the ghost of an alignment replaying itself. Each time, the readings fell just above the threshold of noise, daring skeptics to look away. And so, the controversy lives on, suspended between faith and doubt, between proof and pattern. Maybe 3 Atlas changed nothing. Maybe the alignment was an illusion stitched together by coincidence, software errors, and human imagination. Or maybe, for one brief moment, an interstellar traveler brushed the sun's electromagnetic veil, and the entire planet, from ionosphere to mantle, shuddered in recognition. The data still hums quietly, the instruments still whisper in low frequencies, and the scientists still argue. Because the greatest controversy of all isn't what happened in July 2025. It's whether humanity is ready to admit that sometimes, even in the language of physics, the universe still speaks in riddles. Speculation. Is 3I Atlas acting as a catalyst? By the time the dust settled from the 2025 alignment, one question had emerged that refused to fade. What if 3I Atlas wasn't just a bystander? What if it acted as a catalyst, not in a chemical sense, but in a cosmic one? An agent that didn't create energy, but redirected it, amplifying processes already in motion. Even the word catalyst made traditional astronomers uneasy. Yet when data from solar probes, geomagnetic monitors, and seismographs were layered, a strange symmetry took shape. Something about the interstellar object's passage through the sun's meridian seemed to have coordinated phenomena that normally drift out of sync. Plasma waves, ionospheric hums, seismic tremors, even tiny shifts in cosmic ray flux. The alignment didn't look explosive, it looked reactive. Catalysts in chemistry lower the energy threshold required for reactions to occur. They don't force change, they make it easier. The same analogy began to surface in heliophysics papers attempting to explain the July 2025 anomalies. If the Sun and Earth already exchange energy continuously through magnetic and plasma coupling, perhaps 3I Atlas temporarily reduced the threshold for that exchange, enhancing sensitivity between the systems. The first to float the idea publicly was Dr. Yelena Korovin, a plasma physicist at Moscow State University. In a preprint titled Interstellar Catalyst Hypothesis, Non-Thermal Mediation in Solar-Earth Coupling, she argued that 3I Atlas, by crossing the heliospheric current sheet at near perpendicular orientation, could have created a localized region of enhanced magnetic reconnection. In simpler terms, it might have pinched the Sun's magnetic field, causing it to snap more efficiently along that line of longitude. Imagine the heliosphere as a vast ocean of magnetic tension, Korovin wrote. When an electrically charged body enters that current, even a small one, it can distort the local topology. That distortion propagates outward like a pulse, and if the pulse reaches a resonant body, Earth, for example, it may trigger sympathetic oscillations. Her argument wasn't that 3I Atlas caused anything supernatural. It was that geometry and conductivity alone could magnify an otherwise undetectable connection between Sun and Earth. Critics predictably dismissed it as overreach. The object, they pointed out, was too small, likely only a few kilometers wide, to influence solar-scale plasma. The Sun's magnetic field dwarfs such intruders by orders of magnitude. It's like dropping a paperclip into a hurricane, one reviewer mocked. But Korovin's supporters countered with a subtle point. Scale doesn't always determine impact. In nonlinear systems, small perturbations at critical points can trigger disproportionate effects. The Sun's magnetic current sheet, a razor-thin region of electric reversal that snakes through the heliosphere, is notoriously unstable. Even minor disturbances can cause waves and kinks that ripple for astronomical distances. What if 3I Atlas crossed at precisely the wrong moment, amplifying those ripples? The hypothesis gained traction when analysts re-examined Parker Solar Probe data from the days leading up to the alignment. The spacecraft, flying deep within the solar wind, recorded a distinct structured pattern of plasma oscillations, evenly spaced like the harmonics of a vibrating string. The period of those oscillations? 7 minutes. The same frequency later observed in Earth's magnetic and seismic data. To Korovin and her peers, that was the smoking gun. Resonance doesn't require contact, she said in a later interview. It requires timing. The object passed through the current sheet exactly when the Sun's oscillations matched the Earth's magnetospheric harmonics. It didn't force the system, it synchronized it. In other words, 3I Atlas may have acted as a tuning fork, briefly bringing two vast energy systems, solar and terrestrial, into phase. Supporters of the catalyst theory pointed to a curious observation. While most solar alignments come and go unnoticed, this one coincided with an almost eerie quiet in the Sun's output. No flares, no CME, no dramatic storms. Yet Earth responded as though something had struck it. It's the absence that's suspicious, wrote Dr. Rafik D'Souza, a heliophysicist from India's PRL. The system acted as though energy had been delivered, but there was no visible source. The simplest explanation is that energy was redistributed, not emitted, the hallmark of catalysis. D'Souza proposed that 3I Atlas's composition might hold the key. Early spectroscopic studies showed traces of metallic ions, nickel, cobalt, even charged carbon chains. If the object carried a residual magnetic field, it could have interacted with the solar plasma dynamically, acting like a moving inductor. As it sliced through the current sheet, its magnetized sheath may have concentrated field lines, creating a transient plasma lens. Such a lens, in theory, could focus the Sun's magnetohydrodynamic waves into narrower beams. If one of those beams intersected Earth's orbit, even fleetingly, it could have triggered the electromagnetic resonances observed across the Pacific. To skeptics, this was fantasy. The heliosphere isn't a laser, scoffed astrophysicist Dr. Jared Kim, and 3 Atlas isn't a mirror. You can't focus plasma waves like light through glass. Yet space plasma isn't entirely chaotic. Observations from Voyager and Ulysses showed that charged bodies from comets to asteroids can indeed shape the solar wind, forming shock cones and coherent wake structures that extend millions of kilometers. Those wakes can align with magnetic field lines and even carry induced currents far from their source. If 3I Atlas was unusually conductive, say due to high metal content or an ionized tail, its wake could have acted as a temporary antenna, broadcasting perturbations through the heliospheric medium. And if those perturbations happen to match the Earth's natural resonant frequencies, amplification, not causation, would follow. Other scientists proposed even more exotic mechanisms. One idea, dubbed the flux mirror hypothesis, came from theoretical astrophysicist Dr. Lucas Chen. He suggested that 3I Atlas's passage through the sun's equatorial field might have created a flux mirror, momentarily reflecting part of the solar magnetic field back toward the sun itself. This feedback could have created a standing electromagnetic wave that momentarily encompassed the inner planets. It would be like two strings vibrating in opposition, Chen explained. If Earth's magnetic alignment matched that wave, the planet could experience harmonic excitation, not from new energy, but from reflected solar energy. No one could prove it. But the math describing it fit eerily well with the timing of the 7-minute oscillations. By late 2025, a small group of scientists calling themselves the Catalytic Network began compiling all known data from the event. Their model proposed that 3I Atlas's role wasn't energetic, but informational. Its motion through the solar current sheet introduced a disturbance pattern, a coded geometry that propagated through plasma, subtly reordering energy flows. The Earth, positioned in resonance with that geometry, responded naturally, like a tuning crystal, vibrating when struck by sound. They likened it to the way a conductor's baton coordinates an orchestra. It doesn't play the music, but it synchronizes every instrument. To many, it was a poetic metaphor masquerading as physics. Yet the metaphor explained something no standard model could: why so many independent systems, from solar oscillations to oceanic infrasound, showed coherent timing. The alternative, some argued, was more unnerving still. What if the pattern wasn't accidental? What if 3I Atlas carried intrinsic electromagnetic properties, a structure or field configuration capable of interacting deliberately with stellar environments? Those whispers reignited the memory of Oumuamua, the first interstellar visitor detected in 2017, whose acceleration had also defied simple explanations. Some had speculated that Oumuamua might be a fragment of artificial origin. That theory was dismissed then, yet now, under the glow of the 2025 anomalies, it resurfaced quietly. One anonymous white paper circulated among researchers suggested that if 3I Atlas were an artifact, a remnant of unknown design, it might have been engineered to amplify magnetic coupling between stars and planets, perhaps as a means of communication or observation. A cosmic relay, the author called it, an object that doesn't speak but listens and makes the medium itself sing. Mainstream journals refused to publish it, but the idea lingered. Even among conservative researchers, there was a sense that something about the event had defied the normal order of cause and effect. If the sun's field, Earth's magnetosphere, and an interstellar traveler had truly synchronized, however briefly, then the universe had demonstrated an unexpected property, that distant systems could become entangled not through energy, but through geometry and timing. In this view, 3 Atlas was neither visitor nor invader, but catalyst, a bridge across scales, linking the behavior of plasma, magnetism, and geology in one fleeting harmonic. No proof exists, and perhaps none ever will. Yet those who study the data often describe a strange feeling, as though the event itself were alive with design. Everything lined up too perfectly, too elegantly, too synchronously. Maybe that's the danger of looking too long at coincidence. Patterns begin to look like intention. Or maybe it's the other way around. Maybe intention hides inside what we call coincidence, waiting for alignment to reveal it. For now, the official stance remains conservative. 3 Atlas is a naturally occurring interstellar body, and any terrestrial resonance was coincidence. But the raw data whispers something subtler. The frequencies didn't just coincide, they harmonized. Perhaps the universe doesn't need deliberate agents to act like catalysts. Perhaps some alignments, by their nature alone, awaken hidden couplings between worlds. And if that's true, then 3 Atlas didn't just pass through the solar system, it played it. For one brief movement in July 2025, the cosmic orchestra tuned itself around a single wandering note, and Earth, whether by chance or design, was listening. Future predictions and testable consequences. If 3I Atlas truly acted as a catalyst, a temporary conductor linking cosmic and terrestrial systems, then its influence should not have ended in 2025. In science, every extraordinary claim demands an ordinary test. The challenge now is turning what seems mystical into something measurable. Theories are fragile things. They either die in silence or survive in data. And for those still studying the 3I Atlas event, the data may yet have more to say. The first prediction emerging from the catalyst hypothesis is cyclical recurrence. If the July 2025 alignment produced resonance between the Sun, Earth, and an interstellar object, then similar conditions should yield similar results. The cosmos repeats itself with clockwork precision. Magnetic cycles, orbital geometries, solar oscillations. Each recurrence offers a chance to test whether resonance alone is sufficient to spark the same planetary responses. The next expected test comes soon. In early 2026, the Sun will enter a phase of heightened magnetic instability as solar cycle 25 climbs toward its peak. Around that same time, the heliospheric current sheet, the magnetic surface that snakes outward from the Sun, will flatten, creating long periods when Earth lies directly within its flow. If 3I Atlas's passage truly amplified coupling through that sheet, then similar magnetic disturbances should appear even without an interstellar trigger. This gives scientists a baseline. If resonance effects reappear, they are natural solar phenomena. If not, then 3I Atlas's alignment may have been unique, an external influence impossible to replicate. A second, more specific prediction involves temporal lag. Data from 2025 revealed consistent time offsets between solar and terrestrial responses, particularly the 36-hour delay between magnetospheric dips and seismic microevents. If the same delay appears during future solar perturbations, that timing becomes testable evidence of magnetoseismic linkage. Researchers plan to watch for this during upcoming solar storms, comparing KP index fluctuations with microseismic activity in known conductive regions like Tonga, Chile, and the Aleutians. To separate coincidence from causation, teams from Japan, Finland, and the United States have begun establishing ultra-deep seismometer arrays synchronized with magnetometers and atmospheric pressure sensors. Their data will be time-stamped using independent atomic clocks, removing the ambiguity that plagued the 2025 analyses. If microtremors increase within that 36-hour window following magnetospheric excitation, and if their frequencies match the 0.27 Hz specific hum recorded during 3I Atlas's passage, the evidence for coupling strengthens. Another test concerns the ionosphere's memory. After the alignment, satellite readings showed plasma oscillations persisting for days, long after solar conditions normalized. If Earth's upper atmosphere retains resonant modes excited by external pulses, those modes should occasionally reappear, even without solar storms. Instruments like ESA's Swarm constellation and NASA's Gold mission are now tasked with scanning for low-frequency electron density waves, particularly those repeating at 7-minute intervals. If such waves recur, faint but coherent, they could signal that the planet's electromagnetic shell was permanently tuned by the 2025 event. Meanwhile, radio astronomers are preparing to test another anomaly, the drifting frequency known as the Whisper. Its downward sweep from 19.3 to 18.7 MHz was one of the event's most puzzling signatures. If 3I Atlas's interaction with the solar current sheet generated that emission, then future crossings by other interstellar bodies should produce similar radio songs. The Vera Rubin Observatory in Chile, operational in 2026, will scan for such visitors. When the next hyperbolic object enters the inner solar system, radio observatories worldwide will watch its path for repeating spectral drifts. Even one recurrence of that pattern would elevate the event from curiosity to phenomena. The catalyst model also implies something profound about planetary sensitivity. If electromagnetic resonance can modulate seismic or atmospheric processes, then smaller versions of the same effect should occur continually unnoticed. Researchers are now building models to test whether subtle solar patterns, not just storms, but quiet oscillations, correlate statistically with microseismic noise. If correlations persist across years, the theory evolves from anomaly to physics. There are also gravitational consequences to test. During the 2025 alignment, gravimetric satellites like GRACE-4 detected minuscule variations in Earth's field, density flickers of 0.1 parts per billion. The readings were dismissed as noise, but if similar flickers recur in sync with magnetospheric activity, they could reveal how electromagnetic stress influences mass distribution in the crust. The Next Generation Geodesy mission, NGGM, scheduled for launch in 2027, will measure gravitational changes with tenfold precision. If flickers align with future solar pulses, it may confirm that magnetoelastic coupling, the ability of magnetic stress to subtly distort matter, is real. To test deeper coupling, scientists are turning inward. The magnetic sensors at the European Infrasound Array, designed to monitor low-frequency atmospheric vibrations, will now be used to search for Earth's free oscillations, natural planetary ringing modes that may resonate with solar periodicities. If identical frequencies emerge simultaneously in atmospheric and deep Earth data, it would prove that both regions respond to the same external forcing. One controversial proposal, still in review, involves monitoring neutrino flux. Some physicists theorize that changes in solar magnetic topology during 3I Atlas's passage might have subtly altered neutrino scattering rates. Neutrinos can pass through the Earth unhindered, but if their flux fluctuates with solar current geometry, that could provide a new window into magneto-nuclear interactions between the Sun and its surroundings. The Super Kamiokande and IceCube observatories are preparing joint analyses for this purpose. For skeptics, these predictions are where the hypothesis must stand or fall. Theories survive not through poetry, but through falsifiability. If no recurrences, no delays, no resonant modes are detected, the 2025 event will fade into the long archive of unrepeatable anomalies, curiosities like ball lightning, cold fusion, or the Tunguska blast. But if even one of these signatures reappears, the 7-minute Schumann beat, the radio whisper, the gravity flicker, or the 36-hour seismic lag, it will mean something larger is at play. Even cautious scientists admit that 3I Atlas offers a rare opportunity for long-term prediction. The object's projected path takes it toward the outer solar system, but gravitational modeling suggests it will cross the ecliptic plane again around 2032, near the orbit of Jupiter. If it retains its charge or composition, its next solar encounter could produce another measurable resonance. Spacecraft positioned along that longitude, particularly the upcoming Interstellar Medium Mapper, IMAP, could test whether the Sun's field distorts again in its wake. If a second pulse appears, the evidence would become undeniable. There's also the question of delayed effects. If 3 Atlas induced a redistribution of electric potential in the ionosphere, those changes could take years to propagate fully through Earth's systems. Long-term atmospheric data might reveal gradual shifts in lightning frequency, jet stream behavior, or electromagnetic storm clustering. Already, climatologists have noted an 11% increase in upper atmospheric lightning over the South Pacific since the alignment. Whether that's coincidence or aftermath remains open. Geophysicists are also watching Tonga and Chile, the twin poles of the 2025 resonance. If deep harmonic tremors resume at similar frequencies even years later, it may indicate a persistent reorganization of subduction stress. The same seismometers that recorded the descending waves will continue to monitor for repeating patterns. Should they detect identical 7-minute pulses again, it would suggest that the crust retains a form of memory of electromagnetic forcing. Beyond physical tests, researchers are beginning to consider the informational ones, the search for patterns not in events but in timing. Some have proposed that if resonance-based coupling is real, global electromagnetic noise should display periodic self-similarity, fractal recurrences separated by specific ratios. Artificial intelligence models trained on terabytes of magnetospheric and ionospheric data are now combing through decades of archives to find echoes of July 2025's pattern. The early results are startling. Faint, repeating harmonics separated by exactly 3.5 years, a rhythm that predates 3I Atlas's discovery. If verified, it would suggest that interstellar interactions like this aren't unique. They're part of a longer cycle woven into the fabric of the solar environment. In the end, the testable consequences may be less about proving the catalyst hypothesis and more about redefining what influence means in a planetary context. The Earth doesn't exist in isolation. It swims in a sea of magnetism and plasma. The line between space weather and terrestrial weather may be thinner than anyone imagined. If the predictions hold, future space weather models may no longer stop at the ionosphere. They'll extend downward into ocean currents, seismic probabilities, even biological rhythms. There are hints already. Spikes in Schumann resonance have been tentatively linked to changes in animal migration and human circadian cycles. If 3i Atlas amplified such global frequencies once, could subtler effects ripple through life itself? That's speculation bordering on metaphysics, and yet it's precisely what the next decade of monitoring will address. Satellites, seismographs, radio telescopes, and gravitational sensors, all watching, all listening, waiting for the faint recurrence of that July hum. Perhaps nothing will happen. Perhaps the event will remain a ghost, a one-time cosmic chord fading into noise. But if the hum returns, if the data align once more, solar oscillations, magnetospheric waves, and deep Earth tremors vibrating in perfect sync, then the 3i Atlas event will no longer be an anomaly. It will be the first verified example of planetary resonance induced by an interstellar catalyst. And that realization will force science to look beyond its old borders. The next time an object drifts in from the galactic dark, we'll know to listen, not just with telescopes, but with the whole Earth as the receiver. Because if the 2025 alignment taught us anything, it's that sometimes the universe doesn't shout its secrets. It whispers them in 7-minute pulses, in faint harmonics beneath the sea, in patterns that only reveal themselves to those patient enough to wait for the next note. Implications: cosmic terrestrial resonance. When scientists first began compiling the July 2025 datasets, they expected to find error, not evidence. No one truly anticipated what the numbers implied once layered together, that the boundaries between the heavens and the Earth are less distinct than we've ever imagined. What happened when 3 Atlas crossed the sun's meridian wasn't merely a curiosity of plasma physics or a coincidence of timing. It hinted at something far deeper, that resonance, not distance, might be the true bridge between cosmic and terrestrial realms. The term cosmic terrestrial resonance began as shorthand among data analysts. It now occupies a precarious space between physics and philosophy, a concept suggesting that planetary systems, stellar magnetism, and even the deep Earth can synchronize through shared frequencies. To many, this sounds mystical. To others, it is the missing piece in our understanding of planetary behavior. The idea that energy doesn't just travel through matter, but through coherence. At its core, resonance is simple. When two systems share a natural frequency, one can transfer energy to the other with extraordinary efficiency, like one tuning fork setting another into vibration across a room. Extend that idea to the scale of planets and stars, and the implications are staggering. If 3i Atlas acted as a catalyst in July 2025, then what occurred wasn't a transfer of mass or heat, but a synchronization of rhythm. The sun's magnetic pulse aligning momentarily with Earth's natural oscillations, amplified by the object's traversal of the heliospheric current sheet. The effects, electromagnetic distortions, harmonic tremors, and ionospheric inversions, might represent the visible traces of that synchronization. To traditional geophysics, this was almost heretical. Earthquakes arise from tectonics, auroras from magnetism, and the two belong to different domains. But the data refuse to separate neatly. When solar oscillations, Schumann resonances, and deep Earth tremors all follow the same timing, 7 minutes, 14 minutes, 36 hours, coincidence becomes an insufficient language. The resonance hypothesis redefines causality itself. It suggests that Earth doesn't merely receive cosmic energy, it participates in a larger symphony of fields. Every solar pulse, every plasma ripple, every cosmic ray burst might reverberate through the planet's structure, modulating it in ways subtle but cumulative. If this is true, it alters our very understanding of planetary evolution. We have long treated Earth as a closed system, driven by internal dynamics, heat from the core, rotation, convection. Yet resonance implies permeability. The planet's cycles, geological, magnetic, even climatic, might be co-regulated by rhythms beyond our atmosphere. Already, researchers are finding hints. Statistical reviews of geomagnetic data show recurring correlations between solar polarity shifts and long-term volcanic episodes. Sediment records reveal millennia-scale periodicities matching solar activity cycles. What if these aren't coincidences, but expressions of a constant dialogue? The Sun and Earth exchanging signals across magnetic and gravitational bridges? The implications stretch beyond geology. If Earth's electromagnetic environment can resonate with cosmic frequencies, then so can the biosphere that evolved within it. Life. From migratory birds navigating magnetic lines to human circadian rhythms entrained by Schumann resonance, may be more deeply coupled to solar cycles than we realize. Some neurobiologists are already exploring whether fluctuations in global electromagnetic background correspond to variations in brainwave coherence, collective sleep patterns, or even global mood cycles. That might sound like pseudoscience, but the data are slowly accumulating. During major geomagnetic storms, hospital admissions for cardiac arrhythmias increase. Cognitive performance fluctuates with geomagnetic quietness. Even mass migration patterns among animals appear to anticipate solar activity changes. If resonance can transmit mechanical energy across space, why not biological entrainment across species? 3I Atlas, in this context, becomes not an anomaly, but a messenger, a reminder that cosmic and terrestrial systems aren't isolated actors, but members of one electromagnetic continuum. The interstellar object may have simply revealed the hidden connectivity always present, but rarely excited into view. Some scientists now call this the field ecology of the solar system, the idea that every planet, moon, and object participates in a shared electromagnetic environment shaped by the sun's pulse. The discovery isn't mystical, it's mechanical. Every atom of rock and air is in essence a conductor. Every shift in solar magnetism threads through that network, however faintly. What 3I Atlas provided was not new energy, but new coherence, a realignment that briefly allowed Earth to ring audibly within that cosmic field. The philosophical implications are profound. Humanity has always treated the cosmos as distant, indifferent. The resonance model hints otherwise, that Earth's processes, even its heartbeat-like tremors, may echo the rhythms of the sun and beyond. We are not observers of the universe's pulse. We are its instruments. Yet such a perspective unsettles more than it comforts. If resonance shapes the planet, what happens when the frequencies shift? The sun's cycles are not constant, they evolve. Galactic conditions, cosmic ray flux, interstellar plasma density, change over time. If Earth's deep systems truly respond to external rhythms, then the planet's stability might depend on cosmic weather far more than we ever thought. Some models already suggest that during periods of intense solar activity, subtle stress redistribution occurs in subduction zones, leading to clusters of shallow earthquakes. Others propose that long-term magnetic quiet phases could alter atmospheric circulation, contributing to climate transitions. If resonance is real, it could serve as the missing bridge linking astrophysical cycles to terrestrial epochs, the reason glacial eras, geomagnetic reversals, and even mass extinctions often coincide with cosmic events. But the 3 Atlas resonance also suggests something more delicate, that synchronization doesn't always destroy. Sometimes it harmonizes. The July 2025 tremors never turned catastrophic. They manifested as deep hums rather than fractures, oscillations rather than ruptures. It's possible that resonance can release tension safely, diffusing stored energy through harmonic coupling instead of sudden failure. If that's true, cosmic resonance might act as a planetary stabilizer, preventing chaotic buildup within Earth's system. The sun's gentle pulses, echoed through the magnetosphere, could function like a drummer maintaining tempo, ensuring Earth's internal beats never drift too far out of phase. In this light, 3I Atlas was not a disruptor, but a metronome, briefly amplifying a universal rhythm that has always been there, keeping the planet in tune. There are other implications, subtler still. If electromagnetic resonance connects distant systems, then communication across astronomical distances might not require transmission of information in the conventional sense. Instead of broadcasting energy, advanced civilizations, if they exist, could exploit field coherence itself, embedding signals in the rhythm of magnetic oscillations. The alignment of 3i Atlas might have been natural, but the mechanism it revealed could be universal. Resonance as communication. In a sense, Earth heard the Sun more clearly during that alignment, and perhaps for the first time the Sun heard back. But speculation aside, the practical implications are immediate. Space weather forecasting may need to evolve beyond monitoring flares and CMEs. If subtle geometric alignments can modulate magnetospheric response, then planetary orientation, interplanetary magnetic connectivity, and even distant cosmic events could become predictive variables. Future observatories might model Earth's resonance envelope the way meteorologists model jet streams, tracking zones of electromagnetic vulnerability where coupling intensifies. For planetary defense, this matters. Satellites, power grids, and communication systems might not fail only from visible storms, but from unseen harmonics, long, slow waves that subtly alter field intensities before any flare erupts. Understanding cosmic terrestrial resonance could transform how we shield technology, predict blackouts, or detect hidden precursors of geomagnetic stress. Yet beneath the science lingers something older, a rediscovery of connection once lost in the mechanistic worldview. The ancients spoke of music of the spheres, the idea that celestial motions produce inaudible harmonies guiding the world below. For centuries, it was dismissed as myth. Now, through data rather than divination, the notion returns in scientific form. The frequencies are real, the patterns measurable. The universe may indeed play a song, one so vast and slow we've only begun to perceive its rhythm. Cosmic terrestrial resonance doesn't demand belief, only attention. The patterns are there for those willing to listen. In the magnetic oscillations that sweep through the ionosphere, in the deep tremors whispering beneath the Pacific, in the faint pulses echoing across the heliosphere. The implications reach not just across space, but into consciousness. If we are part of that resonance, then awareness itself may be an emergent property of coherence, the mind mirroring the same harmonics that govern stars and atoms alike. In that view, the 3i Atlas alignment wasn't merely a scientific event, it was a glimpse of a unified system, a single vibrating field, linking the cosmic and the terrestrial, the macro and the micro, the known and the unknowable. For now, the instruments keep recording, the waves keep passing, the data continue to hum softly, whispering of a universe that does not separate its parts but lets them resonate together, sometimes visibly, sometimes only as a tremor in the deep. Perhaps that's the final implication of 3i Atlas's passing, that resonance, not gravity, may be the truest thread weaving cosmos and world. A reminder that beneath all apparent chaos lies rhythm, and that Earth, far from isolated, is forever part of the music.